Um, got the YouTube stream started up. I I wasn't sure if I should stream this to YouTube or not, but I'm gonna do it and see how it goes. Um, yeah, including the audio from the videos that we're going to watch. Wait, I am logged in. Let me, okay. Just so I have something to cover the screen with. Let me bring this up. I'm not sure I'm logged into the account. Okay. Yes. Okay, I'm gonna hold off until Ian Suki gets here, though. So she's gonna have to sit here in suspense for a few minutes. Let me get, you know, I probably should have drunk water before I went live. Let's fix that and drink some now. Ooh, and I meant to test this command. Okay, nice. There it is, Stuki. Thank you for the raid. Thank you for organizing this as well. Well, welcome in, people. So, I think you all know what's happening. We're just gonna the baton has been passed to us, and we're gonna run it forward. I guess I should get in the Discord, right? Actually, I don't know. Can I kill something first? Let me log into Daisy quickly. Wait for the next few videos to be the same. If I see or someone calls out that a video's been seen before, I'll skip it. But I've mostly been lurking and half paying attention to the other people who have been doing this, so I don't know all the ones that have been gone through, but I was just paying attention to what's happening on Suki's channel, at least for the last while. So if it's one of those videos, we shouldn't, or I should like recognize it. I guess let's get a video in here. Okay, Zach, you called it. I recognize this. I guess I'll add it to watch list in case someone else wants to watch it. I don't think we should do the same video like twice in a row, but if there's like a delay, I would think it's fine. Okay, this I don't recognize, and it sounds pretty cool. High school, undergraduate, graduate, or I guess let's start with the title. What would you actually say if a warp drive passed you? General relativity, physics, Python simulation, astrophysics, space, warp drive. Let's read the little prelude. Warp drives have been the heart of many famed sci-fi shows, including Star Trek. Even if we could build them, how they actually work. And what would someone see if a ship traveling faster than light passed by them? Contrary to intuition, one would see two ships appearing out of nothing. Wait. I need to back up. I already forgot. I'm so focused on reading it out loud and not sounding weird that I wasn't actually understanding the words that were being said. But even if we could build them, how they actually work. And what would someone see if a ship traveling faster than light passed by them? I feel like you wouldn't see anything. I guess that maybe on a delay you might see something. Contrary to intuition. Say stuff. Thank you for the follow. Contrary to intuition, one would see two ships appearing out of nothing, one traveling backwards into the past, and the other traveling forwards into the future. That is contrary to intuition. This video works out why from scratch. A superliminal ship. Okay, people have been using this word so much, I feel like, in the last few months, and I have no idea what it means. Today that changes. Oh, faster than the speed of light. Huh. Okay. But what does subliminal mean? Is that, like, I feel like that L. Does it have another meaning? It feels like a psychology term or something. I don't know. That doesn't matter. Say stuff, I'll get right on that. Oh, okay, $10. Yeah, subliminal messaging. That's what I was thinking of. Subliminal. Never mind. Okay, different word. A superluminal ship outruns its own light, so the arrival time of its light race has a minimum. And rays emitted both before and after that moment reach the camera in sequence. I guess it was, Arad. The rendered flyby traces light from an extended ship, while the schematics alongside it uses a simplified point ship. Okay. Let's see what happens. How long is this? Wait, what? How you're gonna explain this to me in 2 minutes? Okay. This is ambitious. Use pause online notes for Calc 3. I love pause online notes. Professor's not very good to be polite about it. That happens. Gird your loins, everyone. Here it comes. Yep. Ooh, potential volume warning. I don't know how loud this is gonna be. We'll go half volume to be safe, and I'll adjust it as we see how loud it is.
You see two ships, but there's only one ship. So how does the Alcubierre drive work? The ship is encased in a bubble of extreme space-time curvature, and it works by constantly contracting the space in front of the ship and expanding the space behind it, so the bubble propagates forwards. The ship itself is at rest inside the dive. However, building such a ship would need exotic matter. Okay, so why are there two ships? The superluminal ship outruns its own light, forming a cone similar to a Mach cone formed by supersonic ships. And so, no light actually reaches the camera until the ship has gone well past it. Now, the arrival time of the light rays emitted by the ship follows a specific pattern. Rays emitted much earlier on have a longer distance to travel and are received later by the camera. But rays emitted much later still have to travel a long distance as well, so there exists a minimum point just before the ship crosses the camera when light is first received. After the first light reaches the camera, rays emitted both before and after appear in sequence, showing the ship moving forwards in the future and backwards in the past, creating two images. This is encoded in the apparent color of the ship, where blue is the old light emitted earlier on, and orange is the new light emitted later.
Okay. This video was an emotional roller coaster. When I first started it, I did not think it would be good. I thought it was going to go way too quick. But it actually, I think, communicates message really well. G-Hive, man, you hate breakups, especially when they try to let you down gently. It's not you, it's me. I just need some space. We can still be siblings. Hi, G-Hive. Ugh, love it. Um, Okay, so there is one thing that I want to listen back to again, which is the part at the very start. He was saying something about the front of the ship being contracted and the back being expanded or something. I want to re-listen to that part because I didn't understand it. I don't know why it's relevant. Like the part around 145?
Color of the ship, where blue is the old light emitted earlier on, and orange is the new light emitted later.
Where's explaining the difference between the old and new? Wait, there's a cat? Is there an Easter egg? Jed meowed. You thought that was your cat? I don't see a cat.
Third
I want to see a
color of the
cat.
ship, where blue is the old light emitted earlier on, and orange is the new light.
Or is this like an abstract cat? I don't know.
You see two ships, but there's only one ship. So how does the alcubierre drive work? The ship is
You see two
encased in a
cats.
bubble of extreme space-time curvature, and
So does spacetime curve depending on your velocity too? I thought it was only mass that curves spacetime.
it works by constantly contracting the space in front of the ship and expanding the space behind it.
Okay, it contracts the space in front, expands the space behind it.
So
What does contracting mean? Is it like if it's like a hyperbola type of thing, would the contraction be in the bottom of the hyperbola and the expansion at the top of the hyperbola, so to speak? Kinetic energy? Oh, that, okay, when you say it like that.
bubble propagates forwards. The ship itself is at rest inside the dive. However, building such a ship would need exotic matter.
Yeah, I I don't know if this part is all that important. If it is important, that the importance is lost on me.
Okay, so why are there two ships?
This part in Ford though is really good. I really like this. Um So we have two things to kind of do for each video. One is a ranking 1 through 10 of the video. The question is, how valuable is this entry to the space of online math exposition compared to the typical video you've seen? We have all these guidelines, with questions that we could consider, but we don't have to. Just gonna scroll through them and skim them. So yeah, we can consider motivation, clarity, novelty, and memorability. I think this video is strong in the memorability department. How valuable is it? I don't know. Oh, there's another question that popped in my head as I was watching it. I wonder if this has a clean representation as a function, this curve, and if that has any significance. So it looks pretty clean. Like, it could be like a hyperbola, even. It might not be symmetric, though. Would it be symmetric? It's kind of... No, it shouldn't be symmetric. Yeah, maybe it should. Yeah. You're probably right, Jed. Yeah, okay, actually, this next part.
After the first light reaches the camera, rays
It's a little
emitted
hard to
both
tell from here,
before
but from
and
here
after
it's pretty
appear in
clearly
sequence,
not
showing the
symmetric.
ship moving forwards in the future.
So maybe it doesn't have a clean function representation, although it still could. Wait for it.
And backwards in the past, creating two images. This is encoded in the apparent color of the ship, where blue is the old light emitted earlier on, and
Does he say it
orange is the
over
new
here?
light emitted
I don't
later.
know. Either way, we figured it out. um, okay, it's the same thing. Okay, so this answers a question I never knew I had, which is, but it's an interesting one. When I was making that command, I kind of was thinking to myself, I wish there's a "what's happening" command for life. If you're ever in like a like a weird situation, do exclamation point what's happening, have it explained to you. Oh, you know what? Before I forget, I do want to jump into the Discord because I do want people to be able to join me if they want. I didn't want to like jump in while you two were still in there, Stooky and Sam, because I didn't want to like make surprise you're back on stream. But if you do want to rejoin and talk too, that's also cool. But if anyone is in the Discord for this event and wants to join, please do. Maybe I should go on open mic if I do this. What will happen? Yeah. Exclamation point, what's tomorrow's lottery numbers? Okay. Let me arrange my Discord so I can see it better. Okay, cool. So I'm not sure what to do for the 1 through 10 yet. Let's start. Yeah, no worries at all, Sugi. I know you've been doing this for a long time now, so please, I like relax and take care of yourself. Okay, so our thoughts. Let's get actual timestamps.
Drive work. The ship is encased in a bubble of extreme.
Okay, so from this will make a great like YouTube short. Actually, I don't feel like it's the best way to express how I feel about this video. Something new that I never thought about. I enjoyed that you can figure out this unintuitive phenomenon? Phenomenon. Phenomenon. Yeah, okay, I think I got it. Phenomenon. Yeah, okay. uh just by thinking about like say it's the reason this happens is basically it's the same reason that like when an ambulance drives by you and the sound gets all weird, right? It's the same. Well, actually, well, no, not an ambulance. It's more like a supersonic thing. Sound from a supersonic object. That had that what that hat hadn't. Hey, Lucas. I was watching your stream for a bit. I saw you playing Trackmania. And by the way, if you're interested in being a part of this on your stream, I bet it'd be possible to like get you in here. If you want to ever like, because there's a couple of days that haven't been scheduled yet. Yeah, it's not my event, so I can't like promise it, but um, I'll make a note to talk to like Stuki about it if they're not listening right now. Uh, basically, three Blue Brown, the YouTuber, has the Summer Math Expedition competition where people submit videos that they make, and all the videos have been submitted, and so there's like a public review period that's happening now, and so us streamers on Twitch and YouTube have gotten together to do a kind of like review-a-thon where we go and try and review as many as we can. So it's basically just watching YouTube videos and giving helpful feedback. Okay, cool. Yeah, I'll hit on Discord when I know more. No, no, no. You just get to freeload and watch other people's content. Wait, does the skip button get grayed out when you start to write stuff? It does! Hey, look at that! I don't know why I'm amazed by that. But that's kind of funny. Why would you spend your time to implement that? I don't know. I'm I'm getting really distracted. Discovers web UI. Yep. Hey, Papadoria. Hey, Syntax. Let's sum. Let's see some. Yeah, this is the video we just watched. It's only 2.5 minutes. It's about like general relativity. What if a spaceship traveling faster than light passed by you? It's a cool one. I do think that the segment from about, what did I say, 23 through 45? Yeah, 45. Wasn't, maybe I should say, I don't understand the purpose. Perspice of the segment. You not find my heart to be interested in physics? That's a lie. It's just like a cool little fact. Like, it's a cool, like, what if? Um, from the video. Do I have anything else to say about this? Like, I don't think so. I guess, we can add in a little thing about the curve for arrival time. Here, the curve for arrival time. Lucas, I think everyone feels that way about their knowledge. I don't know. A lot of these videos are at least trying to be appealing to people without fancy degrees and things like that. So I think you'd be fine, personally, but it's completely like up to you. Okay, I think. Oh wait, we need to figure out our rating now. Um, how valuable is it? The word valuable is interesting. I would say this is a video that makes you go, huh, that's neat. But not much more. And that makes you sit around the 5-ish. I almost did that around it because I just had it on 1 just because I was playing with the slider for fun. And then if I didn't remember to scroll back up and do this, I would have accidentally left a 1. Actually, you can go back and fix your ratings, so as long as I remember to, would be okay. Um, I might. I would love to know why. That, like, I want more about why. It does. It is very exact, Papadoria. I loved it 1 star. I'm kind of wondering about a 4.5 because I'm left asking why about a lot of things. But like, he might not be trying to answer why. Like, that might not be the purpose of what he's trying to do. Save my life, 4.5 stars, or 4 out of 5, 4.5. I don't know. Terrible 5 stars. I think we'll go with 4.5. We can't always come back and fix it. 4 plus pi minus 3. Oh, that's a fun number. 4.14. That's kind of cursed, having like the decimal part of pi with different whole parts. Okay. I think we're going with this. A phaser? It's a thing you set to stun. What the heck is a phaser? Explained by a fly. An arrow and a wave are the same object. A phaser. Rotating one slides the other. This video follows from the idea that Euler's formula to a fruit fly's brain. Follows that idea from Euler's formula to a fruit fly's brain. Okay. Where rotation is performed by 4 scaled waves, landing in shifted positions and summing. Oh, J! Okay. This video is starting out in a deficit. Yeah, I'd love to make YouTube videos too. I've had an idea for one that I want to make. I don't know if I want to do it though. YouTube is really saturated with like really good quality content. It just feels hard to compete. Don is a J hater. I am a J hater. I mean, I don't mind Papadoria's form because it's more clear what the leading digit is going to be. I thought I was saying we have. Yeah, I say that the sentence is constructed a little weirdly to me. It might just be my own fruit fly brain though.
If you
10 minutes, not bad. I guess we can pin these even too. Papadoria, hopefully you can hear the audio from the YouTube too. I fixed this, at least for this stream in particular, you should be able to hear this audio. Look at where the chemistry guys started. That gives me some hope in starting. Like organic chemistry tutor? Quaternion update dropped. 1 I, L, and K, skipping over J. I have to say very first stuff. This is what it is. What is that? I mean, you get good at YouTube by being bad at YouTube. You got to start somewhere. If you go to my YouTube channel and scroll all the way down, I made 2 videos when I first made the channel, and they are embarrassingly bad, but I don't... Like, I want to delete them, but I also don't want to. Anyway, I'm gonna mute my mic and we'll watch this video. I might pause the video and unmute, but let's start watching. Wait, Leo, you know what this is. It's the thing. This is my first shift. Yeah. Oh wait, I need to put the link in the YouTube chat too for the video that we're watching. Yeah, Leo, hop in if you want. Let me set up the screen share so it's hopefully easier for you. Let me put a message in the Discord server too. Okay, I'll hang on for Leo to join before we start it. I feel like I make videos to share random math things that are cool. I also feel like what I have to say is not interesting enough for other people. Not really in the mood to put any actual effort into the creation of them. Oh god, Jed. Okay, we'll try and speed on those push-ups, but say everyone feels like that, and you gotta actually like do it. All right, so you don't have to, but you could just try and get over it and do it. Okay, push-ups. I have new arms for now. So go with the free beat picks? I guess so. 100 squats. I can't do those.
Daniel, it's me.
Leo, how's it going?
Doing all right. I'm you know what? You've got a knack. When Dawn is live, I am sleepy.
I mean, it's my talent.
Some way, somehow. I was just feeling, I'm feeling real sleepy. I don't know. Let's check the YouTube. It's like, oh, Dawn's live. That makes sense.
Ugh.
That's You know, Reggie's also live. If I fall asleep, I'll wake up in her.
Oh, hey, there we go.
I got my AirPods on.
Oh.
I wonder, is it coming out of my nice mic? How do I sound?
Your audio definitely just changed right then. You sound okay. It sounds like you're
Oh, no,
kind
I
of
know,
close, but
Well, no. I'm fixing it.
okay.
Let me fix it. All right, how's this?
Oh, that's nice.
Yeah, it is.
I'm being caressed by your luscious voice right now.
Hello.
Hello.
How's it going? We're just gonna
Beautiful.
take a nice time today and figure out what the hell's going on with phasers. Phaser? I hardly know her. Daniel classic.
Mm-hmm.
Alright, now I'm watching the stream volumes.
So yeah, you should be able to hear it through the Discord screen share, but I know it's easiest for you.
Well, let's see.
Okay.
I don't know what a phaser is, so let's find out. I don't know.
All right. I guess I'm
ready to be like brutal. Who's bad cop? I'll be both.
Okay, I'll be neutral cop then.
Okay, I'll just be all over the place. People won't know how to feel.
This will be great.
Uh-huh.
If you imagine
What
yourself
the heck
as
is
a
it?
point on a map, and you want to indicate a direction and distance to walk along, you'll need two numbers to completely describe it. But we can
I'm not a
actually do
point on a
this in
map.
two different ways. Placing ourselves at the origin, we can either use an XY rectangular coordinate system, or a compass angle theta and vector length a, known as polar coordinates. In fact,
Hey.
Euler's formula gives a natural way to think of both of these coordinate systems not as two real
If only there
numbers,
was a
but as just one complex number.
letter for
with
the
argument
radius.
or angle theta and modulus
For the
or
radius.
magnitude
The
a. We can
80th.
then derive x
Holy-
and y coordinates as cosine
Oh,
and sine
rod,
of theta,
amplitude.
scaled by
That's
a,
cool.
which drops out of calculation when assumed to equal 1. While it might seem strange to use complex numbers to describe directions in real space, there are some advantages to using this parametrization. For example, if we want to rotate a vector by a certain angle phi, we only have to multiply it by another vector with magnitude 1 and angle phi, which simplifies to adding the exponents.
Holy.
Moreover, to compose two vectors as if they're consecutive movements on a map, we just have to add their two complex exponentials together. In this sense, multiplication and addition of complex numbers make it easy to rotate and compose 2D vectors without needing to introduce
Well,
matrices.
that second form's kind of
In fact,
difficult, but
we can also think of complex
Wait, is it? I was too busy looking at chat.
rotate a vector by a certain angle phi.
well, the
we only have to
addition you still have to
multiply it
like
by another
solve that
vector
trig
with
problem.
magnitude 1 and angle
Oh,
phi,
yeah, you
Uh,
have to do a bunch of
simplifies to
identities,
adding
right?
the exponents.
Yeah.
Moreover, to compose two vectors as if they're consecutive movements
Congrats,
on a map,
Doomwood. That's awesome.
just have to add their two
Yeah,
complex
okay, yeah,
exponentials
that's
together.
fair.
Yeah,
In
yeah.
this sense,
Like finding
multiplication
A3 and theta
addition of
3.
complex numbers
Yeah.
make it easy to rotate and compose 2D vectors without needing to introduce matrices. In fact, we can also think of complex numbers not just as parameterizing two-dimensional space, but as parameterizing a sinusoidal function, like sine or cosine. Because these functions are periodic, we only need to specify an amplitude and a phase in radians, which map onto one real and one angular axis. In this case, it's most common to refer to the complex number parameterizing the waveform as a phasor. While this math is certainly
Phasor.
familiar to electrical engineers, the operations of rotation and summation
Oh, so
are
A
just
is
as
the
relevant
phasor?
to us when we move around in daily life, or to any animal
I don't
that
actually know.
swims, slithers, or flies.
Should I back
I
up?
think
Even
he's
the
referring
tiny
to A.
fly
I don't know
knows
if we'll
when it's
ever
Because
moving
get
A
there.
gives you
forwards versus
amplitude
backwards.
and phase. So I guess it's called a phasor. I've not heard this word before though.
Me neither.
Like I think he said A e to the is like the A is the phasor, so because A will be equal to like R e to the I phi, so it gives you the phase and the amplitude.
Oh, it's just the name.
Oh
It's
yeah, I
just
guess
Z.
A does make sense because it does need to have. You would use R for the amplitude purely.
Amplitude and a phase
Huh.
in radians, which map onto one real and one angular
Okay.
axis. In this case, it's most common to refer to the complex number parameterizing the waveform as a phasor.
Wait, no, it is just the amplitude.
While this map
It says Z equals
Well, I
A
think
e
it-
to the
no.
theta.
I think he's referring to it as like A has phase data in it, so A could be complex.
Oh,
And so A could be like R e to
Oh.
the I phi,
okay.
which I'll admit by the video is not very clear. So like bad cop says terrible, good cop says okay. So you highlighted it.
Neutral cop isn't sure how to feel.
Yeah, neutral cop is like doesn't feel strongly one way or another.
Okay, so this would make more sense. Where I think of A as like an initial condition, then, and theta is the thing that you're varying.
Yeah, I guess so. But we'll see what he says. I've actually not heard this word before. We're learning something. Wow.
Yeah. Wow. Imagine that.
You know, you knew you could learn math on YouTube. What are they gonna think of next?
I don't have a single channel to learn math on YouTube, to be honest. So this is new.
So, like, I don't really know how to learn or read, so it's tough. Tough on both counts.
as a phasor. While this math is certainly familiar to electrical engineers, the operations of rotation and summation are just as relevant to us when we move around in daily life, or to any animal that swims, slithers, or flies. Even the
I do all
tiny
those
fruit
things.
fly knows when it's moving forwards versus backwards, and is able to navigate around a room, but its brain wasn't designed by engineers who knew this math, so how does it pull this off?
It wasn't?
To more rigorously
just the
state
pigeons?
the problem of navigation faced by the fly, let's introduce some notation. When a fly moves, it senses motion in its own frame of reference, how fast it's moving forwards, sideways, or backwards relative to its body. We'll call this body-centered coordinate frame Z-self. But to know where it's moving relative to an
Wow.
external landmark,
To know your
for example,
Z-self.
the sun, the fly must convert Z-self from this egocentric frame into a frame
Wow.
fixed to the outside world. We'll call that
Damn, he dropped
Z-world.
egocentric.
We know the direction the fly is heading relative to this landmark. Then, to convert Z-self to Z-world is simply a rotation. We can think geometrically as a rotation by theta, or algebraically, we can write it more compactly
You're
by
my Z-world.
multiplying Z-self by the phasor
Aw.
e to the
Oh,
I
Don.
theta. So there are really three
Oh my
angles
God.
at play here.
I'm gonna fall asleep
Theta,
halfway through
fly
this
trending
video,
in the world.
but
Gamma,
My
the
Z-world
direction it's
too.
moving relative to its
Holy.
own body, and phi, the direction it's actually moving relative to the outside world. On paper, this solves the problem, but in the brain, this computation must be built out of neurons, which imposes constraints on how both the angle and the magnitude of a phasor can be represented. Let's start with the angle. A phasor can be represented as a sinusoidal pattern across a population of neurons. But how many individual measurements from this population do we need to know the phase? One is
Across a
not enough.
population of
A
neurons?
single height on a sinusoid is ambiguous because the same value will
Yeah, I'm not
occur
sure
at
where
two different
this is headed
phases.
either.
But two
well,
measurements
let's see,
separated
yeah.
by 90 degrees, a
Hey,
cosine
Ming.
and a sine, are enough. Together, these uniquely specify the angle. Now, the matter of magnitude leads to a different problem. A neural firing rate can increase or decrease, but it can't be negative. If we represented velocity using ordinary x and y components, each component would need to be positive in one direction and negative in the opposite direction. The circuit could place those values around a baseline, allowing activity to rise above the baseline for positive values and fall below it for negative ones, but that uses up the dynamic range of the firing rate that could otherwise represent magnitude. And here, magnitude encodes speed. So, instead of using two signed components, the fly divides motion across four non-negative channels arranged as two opposing pairs. Each channel k is associated with a fixed body relative direction, beta k. Its activity, ak, is the rectified projection
I gotta
of the
be
fly's
honest, starting
self-motion
about
onto
40
that
seconds ago, I have
direction.
no idea what he's talking about.
Me neither. As soon as we involve the neurons, I don't really know what's happening.
Yeah. But we could keep going. Maybe we'll find out.
Yeah.
Move towards beta k, that channel becomes strongly active. Move in the opposite direction, and it falls to zero, rather than becoming negative. Together, those four non-negative amplitudes preserve enough information to reconstruct both the direction and magnitude of self-motion, as z self equals sum over k of ak times e to the I beta k. Substituting this into our original rotation, and using the fact that multiplying phasors adds their angles, we can derive a formula for z world as sum over k of ak times e to the I times theta plus beta k. Because we're summing sinusoids of the same frequency, the result is another sinusoid of that frequency, and so we can write it as the single phasor a times e to the I phi. The end result is a single sinusoidal waveform with amplitude a and a peak at phase phi, which points in the direction the fly is moving relative to the outside world. In principle, this is entirely possible. Now, let's take a look at how the fly's brain actually solves this problem.
Okay, so wait. Ming and Rod are both pointing out that this looks just like a Fourier series without using the name Fourier series, and I think I agree. It's maybe like a vector interpretation for a Fourier series.
Well, Fourier series, is it? Because they said it had the same, it was sinusoids of the same rate. And a Fourier series would be higher powers of that rate.
Maybe.
But let's see. I mean, looking at the still frame, I guess we have a constant mode, but two constant modes, and they're going in four different directions. I don't know that this is a Fourier series.
Maybe you're
because,
right.
Yeah. I think all of the signs they're talking about have the same rate, so it's not a Fourier series. I think maybe it's just interpolation, and these different directions are a way to maybe get a more robust kind of interpolation of where you're going based on sensing in four different directions, and you average over it. And so if there are errors, it might just be more robust. But I think it's pretty confusing because like a lot of the really a minute and a half ago, like it spent 3 minutes explaining the complex plane and then 0 minutes talking about what they're actually talking about with both the neurons and the sensors. So
yeah.
there's definitely some work could be put in to improve this video for sure. But I guess I would just keep going because it just definitely skipped over some important details.
Yeah, my neurons are not firing right now. They're not phasing.
I never fire. Yo, Ming, we're actually in the Discord if you want to go into the voice channel and also hop in.
Yeah.
Just invite
You're
everybody.
welcome to do that. Hey, Cruz.
We're in the main voice channel.
In the meantime, hey,
Now that we
Colorcone.
have the equation we need to implement, let's get into how we can correspond each of these mathematical terms and operations to the firing activity of neurons and the connections between them. The main characters at hand are the PFN neurons, 60 cells divided into 4 groups, each of which acts like one of these basis vector channels. Our final answer will be given
Hey,
by
Ming.
the activity
Oh,
of
hey guys,
travel
can you hear me?
neurons.
Hey,
Yeah.
yeah. Just need to adjust your level quick.
Respond each of these mathematical
Hello?
to the final activity of neurons and the connections between them.
Oh, you are echoing though.
Characters at hand are the PFN
Oh yeah,
neurons,
could you put on
60
headphones
cells
or something?
divided into 4 groups, each of which acts like one of
Or maybe
these
I just hear
basic
the video
vector
playing. I
channels.
guess I don't hear our
Our
voices.
final answer will be given by the
Ming?
activity of
Hey guys, can you hear me?
Yeah, I think we hear the
think,
video coming through Ming's.
Yeah, I don't have a headset with me right now, and it's
I see.
messing with your voice. So I'll just log out.
Oh well.
Mm. Okay.
Thank you for
Well, do
trying.
give comments in the comments. We'll read it.
Okay.
The Habner. Yeah, so it's some AK plus e to the I theta plus beta k. So it's interesting. These beta k's are all shifts. They're all phase shifts.
Yeah.
And so it's getting. Yeah, but it's phase shifts in space because it's doing like a 2D space thing. Well, anyways, I guess we can keep watching and see what they say about these neurons.
H delta B.
19 cells, which
Shit,
is
let me back up a few seconds because I lost that.
I do not have neurons.
neurons, 60 cells,
PFMD's
divided into 4
nuts.
groups, each of which acts like one of these basis vector channels. Our final answer.
This is
will
how
be
I
given
learn math, by the way.
activity of travel
Yeah,
direction
relating to
neurons.
these nuts.
19 cells.
Yeah,
which
I
receive
just
input
read
from
it
the
and work on my
PFN
Type
and compute
5.
the fly's movement in a world-centered frame. But to get there, we'll need 3 key concepts about how neurons encode information. First, neurons are selective, meaning they respond strongly to some stimuli and weakly to others. Imagine a neuron that prefers one particular heading relative to the sun. When the fly faces that direction, it fires at a high rate, and when the fly turns away, its activity decreases. Secondly, neurons often work together in groups, or populations, to encode more information together than they could alone. In the fly brain, one population of many neurons works together to encode head direction, each of which is tuned to a different angle. One neuron alone doesn't tell you much, but knowing the activity of all of them can give you a precise reading. Finally, because neurons receive inputs from other neurons, they inherit the selectivity of these upstream neighbors, allowing their tuning to be passed on and transformed from one population to the next. Taken together, these ideas make it clear that a neuron's activity reflects what its inputs are tuned to, how strongly those inputs arrive, and how the neuron combines them. We'll see how the PFN neurons viewed in this sense can be thought of as computing our equation for Z world. As we mentioned, there's a different population in the fly brain that functions as a compass, representing the fly's heading angle with a wave whose peak points in the current direction. Each PFN population receives inputs from this compass, but within each group, different neurons prefer different heading angles. So a plot of one PFN population as a function of each neuron's preferred angle looks like a sine wave with a peak at the current heading. As the fly turns, the waves shift so that the bump stays aligned with the heading direction. This shows us how theta can be represented within each of the 4 PFN groups.
This is cool.
But heading is only half the story. PFN neurons also receive self-motion signals, telling them the fly's current velocity. As we saw, self-motion is split across 4 fixed body-relative directions. For each direction, beta k, the number ak is the fly's motion projected along that direction. Move towards beta k, and ak is large. Move the opposite way, and ak falls to 0, but remains non-negative. What we can see is that the motion signal
never
doesn't
do that with
shift
my
the bump
channel.
in a PFN
Never,
population,
no.
but instead it scales the whole wave up or down. In this way, the amplitude of the waveform encodes motion, and the phase encodes heading direction. Neither one interferes with the other. We can write a formula for this as ak rectified times e to the I theta, which already looks like one term in the summation for computing Z world. But how do we ensure that each of these 4 PFN groups points in a different direction? It turns out no extra signal is needed to compute this shift, because it's hard-coded into the anatomy itself, determined by where the axons land. A downstream neuron doesn't receive input from PFN neurons that all prefer the same heading. Instead, it gets inputs from cells in each population that prefer different headings, spaced proportionally to the differences in beta k. The effect is that each PFN population projects to the travel direction neurons with its own fixed offset. Therefore, the arriving wave is shifted over the population axis by a fixed angle, beta k, determined entirely by which PFN population it originates from. This is what we mean by saying that beta K is built into the anatomy. The travel direction neurons then perform the last step and one of the simplest functions of a neuron. They sum these different inputs together. The 4 input waves, plotted over the 4 PFN populations, thus become individually scaled, shifted, and summed together. And because summing sinusoids of the same frequency yields another sinusoid of that frequency, we get the final phasor representation of Z world, A times e to the I phi. The end result is one wave with an amplitude A and a peak at phase phi, which indicate the speed and direction the fly is moving in world-centered coordinates. By now, hopefully you see how each symbol corresponds to a different feature of the fly's navigation system. The heading direction is a population bump input to the PFN. The amplitudes AK function as gain, scaling the activity of each PFN population. The beta K are phase offsets induced by patterns of connection, and the summation is the combination of PFN outputs by the travel direction neurons. Step back and look at what the fly brain is doing. The final population wave is just another phasor, one magnitude and
That's
one
what people
angle.
think when they watch my videos.
Wait, what did he say?
Step back and watch what the fly brain is doing.
But this contains all the information the fly needs to know where it's going in the world and navigate as it needs to. Thank you for watching. We hope you enjoyed the video and learned something, or at least
The cool
gained
picture.
a little more respect for our good friend the fruit fly.
I
Okay.
see. Well, what I would say is that I think technically is rather good. Like it executed on, making the animations and stuff. I think the key thing that, at least for me, that was unclear and basically took the whole video to sort of figure out is like, maybe this is my fly brain, but it needs to be very clear, what's the point of what we're all doing? And when you introduce something like what the neurons are doing, like I'm not even sure he said like what activates a neuron. Sort of staring at the graphic is, I feel like I got a better idea of like, oh, it's like how much light, how bright to that section of the compound eye is what the neuron is. And then all the beta Ks are the offsets.
Yeah.
And it's hard to give a specific piece of advice because it just seemed like, I guess it would be better if it was more clear what the outside, because also in some sense, maybe went too quick or something. I did not, also took as like sometimes like, oh, are we looking at the signal with respect to what it sees? Are we trying to do the signal as like where is the sun relative to the fly? But the signal I was trying to go for was the direction the fly was moving, which seems to like need a little more. Yeah, it talked about coordinate transformations, and I also wonder about the coordinate transformation thing because it talked about 2 vectors in the egocentric view and also in the world-centric view, and then represented those as 2 different lines, when I think, the direction you're moving is really the fixed point, whereas the coordinate axes are the things that can move. Yet it showed sort of 2 different vectors given by that rotation, when maybe it should have shown 1 vector with 2 different coordinate axes that were rotated against each other. But yeah, I really didn't. I guess what I would say is that like some of the story has to be clearer. Like it's like what Ming's saying. What is the problem we're trying to solve?
Yeah.
And then some of the details, especially in the middle, whenever you introduce something, it's got to be clear. It's like, I don't think you can assume that the viewer, at least if the viewer is me, knows what the neurons are firing on. And so it's hard to give specific advice. Maybe, test it out with friends and like see where they get confused, because part of the advice is just execution on explanation.
Yeah.
So it's hard to see. Actually, there's something else. I think Reggie's live right now. I wonder if she wants to review.
Yeah, feel free to like send her a message or while they're in her chat or
Dawn
something.
and I are in Discord chat reviewing a video right now. I showed up and she is punching me.
Of how they work biologically for the purposes of this video and how it relates to the math.
Discord server and join the voice call. Discord for the call. You can keep streaming.
Math. Yeah, that'd be fine.
Should I be streaming?
You can turn it on if you want.
I'm feeling kind of relaxed. I don't think I'm gonna go live.
Yeah, if you just want to chill, that's fine too.
Yeah. I'm feeling good.
I need to get in what Ming said.
I feel like this is the most you've heard my voice since you've never, watched any of my videos.
It's my
so
first
I'm,
time hearing your
good.
voice, actually. I've never heard it before.
It's nice.
Yes.
Hello.
I love this ASMR.
Yeah. I'll go live. This is what I'm writing in a chat. I'll go live if you want to be on my Snook. I was gonna say I'll go live if you want to be on my stream. Name Reggie, age 28. She's got a whole bio in her Twitch. I don't have a bio. Nobody knows anything about me. I'm the mystery man. How would you rate it? I haven't seen the other videos. I would guess. I have a guess of where I would rate it, even though I haven't seen any of the other videos.
So the question is, how valuable is this entry to the space of online math exposition compared to the typical video you've seen?
To the typical video I've seen.
Yeah. So it's subjective.
So it's not based on this. I thought it was based on the other videos submitted. I guess I would just put not as good. Probably. Because I didn't really get it, but maybe you liked it. Yes.
I'm always reluctant to give scores below 5 because I just feel bad about it.
Fan.
Oh yeah.
You're always reluctant to what?
Watch your videos. But also give scores below 5 because I feel bad.
Aw. It's okay, I'll be bad cop. I'm making you do it.
Out of like a 3 feels harsh. I would because I do really like the visuals. If it was you would just like say a 3 exactly.
Probably. I didn't know it was a slider. I thought it was just these things.
I'm gonna go 4. And on your shifts, you can give it whatever you want.
Well, I'm probably not gonna get this video.
Well, I mean, yeah, it doesn't do repeats. But I mean, you could log into the account and edit the vote afterward too.
You can edit the vote afterward? Oh my god, you can come back.
So you can really mess with people if you want. Yeah, it's like it is a really well produced video. That's why I wanted to like bump it up a bit. Reviewing these, you generally can't form a coherent opinion on anything. Dedekine cuts? Oh no, I don't know these. Maybe I'm about to though.
Oh, I like Dedekine cuts. Okay, so I think we might get Reggie's, so should we wait a second for
Oh yeah,
to
sure.
turn on? Alright. You wanna play rock, paper, scissors? We'll just yell it out.
Okay, sure.
Ready? Rock, paper, scissors, shoot.
Rock.
Rock.
Oh.
Damn.
That didn't work.
Okay. You ready?
Yes.
Rock, paper, scissors, shoot. Paper.
Scissors. Ah!
I'm destroyed.
I win.
Oh. I think Koshi's sequence is... Wait, she's gonna do a little code? Okay, maybe we'll just start.
Okay.
Yeah. Alright.
Let's read the little introduction
believing...
first.
I was got an introduction.
Yeah, they all do. Dedekine cuts made easy, intuitive, awesome.
That's how you watch it. I can't read. This is discrimination.
All right. We won't read then.
I don't know. It's too many letters. I'm confused.
All right.
I only know the first half of the alphabet. The second half scares me.
Okay, wait. This thumbnail is
Terrified.
actually incredible. I love this.
Where is Route 2? Yeah, it's a good thumbnail.
Yeah.
Yeah, all these things, they all have better, I feel like, technical execution than I do.
Oh yeah, for sure.
Oh, wow, thanks. Okay, Don's like, yeah, they're all way better than your videos, Leo. I'm
No,
like,
I
"Oh,
have the
damn.
shittiest YouTube videos ever. If
man.
you scroll down far enough on my channel,
Oh, no, it's okay.
I'd rather watch a Leo lectures video than my old
Wow.
videos.
Wow. But he'll settle for watching neither.
All right.
All right, let's
Where
see.
do real numbers come from? What I learned in middle school was the real numbers are like the rational numbers, except they also include the irrational numbers. It's very helpful.
That's cooking.
But one day, during what I can only describe as
cooking.
a mathematical midlife crisis, I realized I had a problem with all of this. Sure, I understand that
Wait,
x
you wanna
squared equals
pause?
5 has no...
Okay.
Oh, Reggie, you made it just in time that we're starting a video,
Oh hey.
so we can start it over.
Yeah.
She muted. You also have to watch the stream on Dawn's thing to see the video we're reacting to. I was just gonna comment. He has a pop filter, and she can't hear us.
I can't hear her either.
I see. Well, she's muted.
Oh,
Guess
I
she
didn't.
muted herself.
My Discord is partially covered.
You got this. Go to settings or something. But yeah, a lot of people commented I need a pop filter for my mic.
Oh, I didn't notice that.
On my recent video, they were all like, "Yeah, you need a pop filter." They said you need to be like this guy who talked about Dedekind cuts. I'm like, damn.
I just got a simple metal
Good
one on
idea.
mine, but if you play with the mic positioning enough, you can usually
Well, he's got
reduce
Boba
it.
Fett and
Oh,
Mandalorian.
the other guy. Yeah.
Where's Baby Yoda?
I don't know.
That's the only thing I care about. Like gear icon, voice, and video. Can check her stream, see how it's going. We could also open her stream in the background. She could
It's
just be-
true. There definitely won't be any delay at all.
I believe in you. Believe in me who believes in you. Believe in Dawn whom I believe in, whomst believes in you. And that's a promise. I'm sure that'll help.
Yeah. The only thing that's missing here is belief, and we're now providing that.
I see. Hello? Can she hear? She undeafened.
Oh. Sure, Rod. Leo did
Oh yeah,
just
wait, I
crash
gotta
the
open
party.
your stream. I gotta see what Arad's saying. Technically, Dawn didn't tell Leo to join. It was the other way around. That's true. I barge in whenever I damn well please. I get in there.
Yeah,
I just
you're a go-getter.
I jump in. I'm a little big. I make a splash.
Mm-hmm.
Gets a little water everywhere. You did it? You can hear? Oh, can you speak? Okay, well, I gotta no. It's not coming through the
guess not.
Discord. The funny thing is I have your stream open, so I heard you. Yeah, I can hear it because I have your stream open.
Wait. Now,
hey.
now.
Oh,
We
it's
gotcha.
got through. Welcome.
What should I should I share my how are you doing that? How are you seeing this video?
So so can you see the video? If you click on in Discord the live thing, it should show you the
Stop
video.
believing in real numbers.
Yeah. They're fake
Okay.
numbers.
True.
Reggie's stream can't hear us.
Can't hear them. Yeah, I know. It was already an ordeal for me to to figure out how to get the sound. Okay, anyway, y'all keep going. I'm gonna figure this out. I'll get there.
But you're so close. Wait, can you see the video? If you just click on
Oh,
the side, the live.
yeah, I can see the video on my personal Discord. I'm just talking about getting the sound to my stream.
Okay.
Which is what I was able to do it before. I'll do it again.
Okay. Well, let's see what Intercontinental, I'm just gonna call him Star Wars math guy, has to say with the pop filter.
Okay, yeah,
Which
yeah.
my sister thinks I need a pop filter, and I was like, no, that's just my voice. Nothing can fix it. It's not.
Your voice pops.
We can't filter that out. You can't filter out my ums and ahs. That's not how that works.
It's a sonic boom every time you say P.
Yeah.
What is that?
All right, let's do it.
Okay.
All right, let's learn real numbers. You haven't seen Dedekind cuts before, right, Don?
No, I've not.
I think they're cool.
Okay.
So, yeah, let's see.
Ming likes them too, so that's
Everybody's
2
got
votes.
everybody's got better production than I do. All these videos, I've noticed.
Hey, Quitch. All right.
Quitch, yeah, I gotta start calling Christian Quitch. I love it. It's so cute.
Oh, do you know?
No, it's Quitch. Don't worry about it.
Okay.
Who knows what the K stands for?
Little Dedekind
Don't
stabs.
stress out.
Complete Attaxium?
true.
I've heard of it. I don't remember what it is. I'm gonna start it.
Where do real numbers come from? What I learned in middle school was the real numbers are
What
like
they
the
came from,
rational
where
numbers,
babies come from.
except they also include the irrational numbers. It's very helpful. But one day, during what I can only describe as a mathematical midlife crisis, I realized I had a problem with all of this. Sure, I understand that x squared equals 5 has no rational solution. But does that mean it has an irrational solution? Who says it has a solution at all? Are we allowed to just invent a new kind of number just because we really want to take square roots? And
Yep.
later on in real
I'm okay with
analysis,
that.
I learned that the real numbers are supposed to be like the rationals, but better. They have this magical least upper bound property, which is the
the rationals were
backbone
better.
of half the course. But again, who says such a number system exists? Does it contain the rationals? Does it behave similarly to the rationals? How does this all work? This is where many students meet something called a Dedekind cut, which
God,
sounds
he's
like a
got the knife
painful
out.
surgical procedure, and the way some textbooks present it, it turns out to be pretty accurate. And at best, it just seems like some sort of mathematical formalism used to justify the real numbers with no real insight. But Dedekind cuts are not arbitrary, they're not some weird technical sideshow. By the end of this video, I will convince you that these are a really
Holy.
natural way to define
He would never
real
do that to
numbers
one of my
make
videos.
perfect intuitive sense. Now, how did I get to
Not
this
once,
point?
not ever.
In the
Nope.
midst of my despair, I went to Nick, our resident animation wizard and mathematical grown-up, and I poured my heart out to him. I told him I wasn't sure I believed in real numbers, and the more I thought about it, the worse things got. I wasn't sure I believed in rational
I need a
numbers
Nick.
either,
I need an
or
animation
negative
wizard.
numbers, and in my darkest moments, I wasn't sure I believed in zero. I told Nick I was
Ooh.
comfortable with positive integers,
Like the Greeks.
and that was it. Everything else had to earn its place and justify its existence. So in
this
this
guy
video,
Chronicle?
starting with just the positive integers and some basic set theory, Nick and I are going to rebuild the entire number line. First, we'll construct the signed integers, then we'll construct the rational numbers, then we'll see why the rational number
doing
line
all of
still
them.
has holes in it, even though it's dense. And finally, we'll use Dedekind cuts to construct the real numbers in a way that actually matches our intuition.
Okay,
should
I've
do
always
the
been confused
complex
about
numbers, do all
the
of them.
density thing. So
Yeah,
I always
maybe.
thought
Well, he'll
dense meant
talk
there are
about
no
it.
holes, but then yeah, we're gonna find out.
Yeah. There are holes.
Yeah. Okay.
Density has nothing to do with holes. Density, density, it feels like you can squeeze things between any two arbitrarily close points. I mean, but you still have possible holes between them. That's
Yeah.
kind of how I see it.
But intuitively, I mean, I don't want to get too into it, but you could even argue that R has holes. You can fit yet more into it if you use like non-standard reals and things like this. But then you lose the least upper bound property. But,
Yeah, that's true.
so like holes is a little subjective, but I feel like it's intuitive a priori that if between any two numbers there's another number, you've got everything. It's just not true.
Yeah, I never formally learned this from a class. I've only kind of like heard things tangentially, so I don't have a good
Yeah.
understanding of any of this.
Well, for one of my videos, I'm going to do this, but I'm also going to do like the Z plus ZQR, but I'm also going to do C, and I'm going to do one more. So I wonder how he does it.
Oh, hey.
I'm not doing Dedekind cuts. I'm doing the Koshi completion way, because I actually think it's more intuitive than Dedekind cuts, but other people disagree maybe. Well, let's see what he's got to say.
I
Yeah.
agree. I agree. Actually, from a computational standpoint, I absolutely agree. Cauchy construction is more intuitive, but perhaps if you just look at the real line, the geometric picture is clearer if you use Dedekind's code.
Yeah.
Okay.
By the end, 0, negative numbers, fractions, and irrational numbers will no longer feel suspicious. They'll seem inevitable. And as a bonus, we'll prove that 13 really does have a 7th root, which is good because I've been very worried about that lately. So let's get started.
6 I can believe. 7 though.
I told Nick I believed in the positive
about
integers and
Bo?
some basic set theory. How was he going to invent signed integers? One approach you could take is to represent signed integers as ordered pairs of positive integers, where the idea would be that 5, 3 represents 5 minus 3, which is positive 2, and then he could use 3, 5 to represent negative 2. 7, 7 would represent 0, and so on. Now in this system, he could represent positive 2 many different ways, and in fact every integer could be represented in infinitely many ways. Now this presents a couple problems. The first issue is that it seems wrong to have multiple ways of representing the same integer. And how do we know if 7, 10 is equivalent to 14, 16, for instance? Or in general, how do we know if A, B is equivalent to C, D? And if we're going to start using ordered pairs
C,
to represent
D's
positive
nuts.
integers, do
I'm
these
sorry.
new positive integers behave in
Oh my
exactly the
God.
same
It was
way
there.
as
He
the
wanted me to
was.
do it.
How do
Yep.
we add them or multiply them?
It was important mathematically.
How do we know if two ordered pairs of positive integers represent the same signed integer? Well, it is tempting
tell
to
me.
say that we can just check to see if A minus B is the same as C minus D, but the whole reason we're in this mess is that due to my
Double
existential
factorial.
angst, I don't know what it means to take 7
Holy.
minus 10 or 14 minus
a big
16.
number.
Double factorial
But
is less
since
than
Nick
single
already
factorial.
knows where this is all going and he remembers his basic algebra, he can just say that these ordered pairs are equivalent if and only if A plus D is equal to B plus C. So 7, 10 is equivalent to 1, 4, but it's not equivalent to 4, 1.
Equivalence
But
class.
4, 1 is equivalent to 5, 2. Now it's easy to check that this relation is reflexive, symmetric, and transitive, so we know that it partitions the set of ordered pairs of positive integers. So the way we represent, for example, negative 3 isn't just 10, 13, it's the entire equivalence class that contains 10, 13. We'll write that as 10, 13 with a line over it, which of course is the same set as 1, 4 with a line over it, which is the same as 5, 8 with a line over it. And likewise, each representation of an integer corresponds to an equivalence class with these ordered pairs. None of these classes overlap, and in aggregate, they contain every possible ordered pair of positive integers.
Okay, wait. Partition means that you split up a set into like disjoint subsets?
So this was the thing I was just writing about, is that I feel like you need to have a real good picture of your audience. And I think the audience who is interested in learning how to construct numbers,
Yes.
it's like, if you say the relation is reflexive, symmetric, and transitive, there's a good chance they don't know what those words mean.
Exactly.
And like similarly, the relation partitions.
Exactly. And
so I feel like they
just
should put
flat
in.
by.
Yeah. Sorry, Reggie, you were saying?
No, I was just agreeing. I just said, oh.
It's
True.
like taking notes in the, what is it, Discord chat. And I think that's a mistake actually a lot of people make in videos. It's just like you have to have a really good concept. Is like, what do they know versus what do they not know, and make sure it comes in order.
All right, I guess just for those on the call, we're gonna have to give this video a 1 through 10 rating relative to other videos on YouTube, and we'll also have a box to give freeform feedback. So just keep that in mind as we watch it.
Relative to what other videos? Like, just
like what you think it does.
online math. Okay.
Yeah, on YouTube in general.
I see. And we can also like leave jokes. I don't know. Maybe it'll brighten their day. I'm just saying it's an option.
I think
Play as
it's
possible.
better than most, or to
Yeah,
outstanding.
yeah, yeah.
Tentatively. Tentatively.
Yeah,
I
we've got
think he's
another
doing a better
17
job
minutes.
with the storytelling than the last one.
Mhm.
But yeah, let's see.
Yes.
next
Especially
issue
the
is figuring-
existential crisis part. I had
Oh,
the
yeah.
same or similar experience.
Well, I still feel that with the real number. Like I don't know a lot of real analysis, but I was reading some real analysis today about sets of uniqueness, which Ming, maybe you know about. And like sometimes I don't know what to make of all the real analysis counterexamples, whether I consider those as platonically real or as kind of like constructed fake things. I don't know. But I guess I'll have to think about that.
in every
We
possible
can talk
ordered
about
pair
it later, but let's finish watching the video.
Yeah, yeah.
Yeah.
of positive integers. The next issue is figuring out how to add and multiply these classes. It turns out that addition is easy. If we want to add a comma b to c comma d, we just add component-wise and get a plus c comma b plus d. We can check that this corresponds to the algebra we knew 10 minutes ago and pretended to forget. But we have to check to make sure this all makes sense. Let's say that instead of using a comma b as the representative from that equivalence class, we use a prime b prime instead. And the same for c comma d. For example, if we wanted to add 6 comma 10 to 7 comma 1, we get 13 comma 11, which matches Nick's assurances that -4 plus +6 is +2. But if we swap out the first pair with an equivalent one, say 10 comma 14, and we replace the second pair as well with an equivalent pair, say 9 comma 3, and add them, we now get 19 comma 17. But notice that this matches our previous answer, since 19 comma 17 is equivalent to 13 comma 11. In general, if we want to add the classes corresponding to a comma b and c comma d, we get a plus c comma b plus d. But if we use two equivalent representations of those classes, we get a prime plus c prime comma b prime plus d prime. Now we know that a plus b prime must equal b plus a prime, and we also know that c plus d prime equals d plus c prime. Add these two equations together, and we get that a plus c plus b prime plus d prime equals b plus d plus a prime plus c prime. And if we group together the terms like this, we can see that a plus c comma b plus d equals a prime plus c prime comma b prime plus d prime. So if we use different representatives from the same two equivalence classes, we get the same result. Now we have to answer the question of how to multiply these classes together. Back in algebra class, we learned that a minus b times c minus d is ac plus bd minus the quantity ad plus bc. This suggests that I might define multiplication as a comma b times c comma d equals ac plus bd, comma, ad plus bc. Again, we have to make sure this makes sense when we swap in different representatives for the same equivalence classes. Let's say we swap out a comma b with an equivalent ordered pair a prime comma b prime. We'll show that if we swap out an equivalent representation for that first number, we get the same answer. You can just as easily show that we can swap out an equivalent representation for the second number too, and therefore we can swap out both numbers consecutively and be confident that we'll get the same answer. Let's quickly write out this proof. We can actually carry out the multiplication the way we defined it earlier, and we need to see if these two equivalence classes are equal. So to check this, we add together the two outer terms, rearrange a bit, and factor, and we use the fact that a prime plus b equals a plus b prime. Multiply out and rearrange, we get the sum of the two inner terms above, which tells us that yes, the two equivalence classes are the same. Now we should check a few other things. For instance, if we just take two positive integers and add them the way we already know how, and then we turn each of those numbers into their new representation as equivalence classes, and then add those two equivalence classes, we indeed get the representation of a plus b. Other things we should check. If we take the equivalence classes corresponding to 5 and 7, for instance, and multiply them together, we get the equivalence class corresponding to 35. We should check the usual properties of integers still hold. 0 and 1 work just like we expect, even on negative numbers. None of these are hard to prove, they're just a bit tedious, so we're going to skip over them. It's easy to get lost in the weeds here, but let's take stock of what we've done. We started with positive integers and the usual addition and multiplication operations on them. We created these new entities and gave them cute little names like -1, 0, +2, and so on. And the new entities corresponding to our old positive integers behave just like the old ones did. As a physicist would say, there's no experiment you can do that can differentiate between the old and the new positive integers. To make things even better, these new negative numbers, and what we're calling 0, behave in exactly the way we want. So I think it's fair to say that we've constructed the integers out of just the positive integers and some sets. And if you followed this so far, I have some good news. The constructions that follow are actually simpler than this one, and they have a more intuitive structure to them. Now that we have the integers, how do we construct rational numbers? The straightforward answer that may have occurred to you is to represent a rational number as an ordered pair. And of course, there are multiple representations of the same rational number, so we have to take all of them. You'll remember from algebra class that a over b equals c over d if and only if ad equals bc. Or as they used to say, about 100 years ago, the product of the means equals the product of the extremes. So we'll say that two ordered pairs are equivalent.
Me neither. I'm glad I didn't.
The outer numbers equals the
I
product
gotta work
of the
that
inner
into my
numbers.
next math rap.
And you can easily show this is an equivalence
Drop
relation.
those rhymes.
So it partitions the set of ordered pairs of integers where the second integer is non-zero. Now, one weird thing to think about is that in this setup,
Wait, what was
a
it?
fraction is a set.
What timestamp is in this video right now?
The order of the
1043.
memes is the order of the extremes. That's definitely not it.
No.
That's not.
Close
No,
enough.
it's fractions.
I see.
Yeah.
You know what? I
Yeah.
Always
tried.
said that.
Okay.
Okay.
Well, what was it then? Damn it. The order of the. Well, anyway.
Of the means? The means. Or the product of the means.
Order. This is the court of the memes.
The order? Was order even in there?
Wait, yeah, what's order in there? Wait, let's go
I don't
back. I want to
think
hear.
so.
I want to
I
hear
don't know,
ours.
actually.
We're at 1043. Let me write that down and then we'll go back.
Okay, sure.
Positive
order of the
where was it?
and some set representations of
A
the
little
same
bit more.
rational ad equals bc.
Here it is.
Here.
Or as they used to say, about 100 years ago, the product of the means equals the product of the extremes.
There's no order in
Wait, the
there.
product of the what? The means?
Oh my god.
Say,
Product
about 100 years
of the
ago, the product of the means equals the product of the extremes.
The means.
I never heard of it, but it's
It doesn't even
interesting.
make sense. What are the means? What?
Yeah, that's what I was wondering.
Product of the means. I don't know.
The mean
I
and
like my
order.
order of the memes.
Would you like to join the order of the memes?
We are part of the order of the memes. We order many extremes. Okay. What I like about the construction of the rationals is they just do this in middle school. They just don't talk about it. Like you turn that bar into a comma, it's just the equivalence class of pairs. It's the same thing as like the last thing. But anyway, I'm sure I'll talk about that.
Okay.
Set of ordered pairs of signed integers, and each of those integers is a set of ordered pairs of positive integers. So a rational number is an equivalence class of ordered pairs of equivalence classes of pairs of positive integers.
Oh wait, I think Floppy has it. Square root
Lofi
AB
has it.
square root AB equals min a comma b times max a comma b.
Square root AB.
Something about
square
geometric
root AB
means.
equals min a comma. What?
Actually, maybe I don't know.
Okay.
Maybe
What? Wait.
oh, I guess it
So
does
it's two-
simplify to AB equals AB.
That's not true.
But there's no CD, right?
I mean, maybe actually.
Yeah.
I don't know.
Yeah, no, it's true.
Actually, yeah,
That is
it is
true.
true. It is true. It is true.
It's
Sorry.
AB times BA, or AB.
That's only
But
one
what-
fraction.
But that doesn't
though.
really help with the fractions, though.
Yeah. I don't
Well,
know.
anyway,
Yeah, what is the point?
it was a
of
good
that?
bar. It doesn't need to make sense. Blow that shit like a cello, you know?
Yeah. Ugh.
We need to define addition and multiplication, and just like earlier, we already know what we want the answer to be. So we can define the addition of these equivalence classes just like you'd expect, and do the same for multiplication. We now have to make sure these operations are well defined. In other words, if you use two equivalent representatives of the same equivalence class, you get the same answer.
Is he
It's a
gonna
good
do them all
exercise
out
to
again?
write out these proofs, but
Yeah, I
we
think
won't
Fan
bore
Okay,
you.
thank God. Very good. Yes.
Interpretation.
I mean, no, yeah, good exercise. Very good skip.
Now, just like earlier, we should make sure that these new objects behave the same way as our old ones did. We should also check the usual properties of rationals, like commutativity and associativity of both operations, and that multiplication is distributive over addition. And we can even show that our new set forms an ordered field. What's a field? It's just a set with two binary operations that behave very nicely with each other. We'll list out the properties, but honestly, whenever I try to remember what they are, I just mentally run through the properties that Q has. And an ordered field is a field with a relation that we'll call less than, which has the usual properties that we're used to from dealing with rational numbers. The one that might look unfamiliar is trichotomy. This means that if you take any two numbers, they're either equal or one is less than the other, and furthermore, only one of those is true. How do we define this relation in the case of the rationals? We can just say that x is less than y if 0 is less than y minus x. And we say a rational number is positive if it can be represented as an ordered pair of two positive integers. And of course, to be thorough, we should check to make sure that this definition of less than complies with the requirements we have above. And we should make sure that these new whole numbers, which consist of an integer paired with the number 1, still behave the same way. Now for the main event, how do we construct real numbers?
Guys, can you pause?
Yep.
Go to the previous slide.
Okay.
Just so you know, I don't order the rationals. I think they're all equally valuable. Just,
Is there, how do we define the less than relation, right? So apparently it says x is less than y if and only if 0 is less than y minus
Oh,
x.
yeah.
That means you already have a notion of less than. I
well,
think
no,
this
it
is
says which
perhaps
means
a
y
little
minus
bit
x can be
debatable.
represented as a pair of positive integers.
Using subtraction we just
Or-
defined,
or-
I think.
Wait, that's as okay. Can be represented as a pair of positive
Yeah,
integers.
y is a pair of,
Oh yeah, okay.
because
So like
we're
a over b,
dealing
where
with
a and b are
rationals, I guess.
positive.
Okay, fair enough.
I see. Yeah, but yeah, that's also slightly unclear because I was thinking of the
I see.
z relation, which that would not be true. But yeah, so that is still technically correct. The best kind.
Okay.
Now for the main event, how do we construct real numbers? Now, it's worth asking if rational numbers are really missing anything. You might argue that since the square root of 5 isn't rational, there's some other irrational number whose square is 5. But my question is, who says that 5 really has a square root? If no rational can be squared to get 5, then maybe that's the end of the story. But it occurred to me one day that there's a very good reason to believe in the square root of 5. You can partition the rationals into two parts. The first part would have all the negative rationals plus the non-negative rationals whose square is less than 5. And the other part would have all the non-negative rationals whose square is greater than 5. So if I can tell you all the numbers less than my mystery number and all the numbers greater than my mystery number, I think it's fair to say that this number is in some sense real. In fact, that's exactly how you can construct the reals. You can just say that a real number is a partition of Q into a lower half and an upper half. This type of partitioning of the rationals is called a Dedekind cut. Now, there's no reason to carry around two pieces of Q if one is just all the stuff to the right of the other, except for possibly the point in the middle, so we'll just work with the left half. So we'd love to define a cut as all the rationals less than a given real number. But this is a circular definition since we haven't yet defined what a real number is. Let's try again to describe this just in terms of the rationals. We want to say that a cut of the rationals is the left half of the number line if we break it somewhere. So the first requirement is that we don't want our set to be the empty set, and we don't want it to be all of Q. That's because the empty set would have to represent negative infinity, all of Q would have to represent positive infinity, and we do not want to include those in our construction. Next, we need downward closure. That is, anytime the set includes one rational, it also includes everything to its left. Finally, we don't want it to have a greatest element. In other words, it does not include its right boundary. So for instance, the negative rationals form a cut. If we include 0 in that set, it now has a greatest element, so that's not a cut. And the open interval from -1 to +1 is not downward closed, so it's not a cut either. If you give it some thought, I think you'll agree that this captures our idea that a cut should consist of every rational number to the left of some imaginary boundary. Now, the idea is that each regular old rational number would be represented by a cut that just consists of every rational number to its left. And if you want to represent something else, like the square root of 5, you would take everything to the left of where this purported number is supposed to be. Anytime you have a hole in the rationals, just grab everything to its left, and that's how you can identify the hole. Now, the super cool thing is that we can define one cut to be less than or equal to another if the first is a subset of the second, and it's strictly less than if it's a proper subset. And oh yeah, we should explain how to do basic arithmetic on these new objects.
Wait, is this a dedicated cut for 1 exactly?
Looks like it.
Okay. I guess there's a reason
Everything
you
less
can't do
than 1.
that.
Yes.
Okay.
It looks like
Everything
that
which
way.
1 owns. Ordered fields are cringe. I don't even know what the fuck they are. I'm just reading Reggie's chat.
Yeah.
It's the same shit that 3 blue 1 brown. I don't think it is. Is it? Maybe it is. I don't know. Do you think
no idea.
Spider-Man prefers... Spider-Man definitely prefers Koshi sequences. What are we talking about? Of course. Ah. Sorry, that was a good question. Or whatever.
Okay.
Addition is easy. Just add together every pair of numbers from each cut. You can show pretty easily that this gives the expected result for rationals. If I take each of the rationals to the left of 1 and add them to each of the rationals to the left of 2, I get all the rationals to the left of 3 and only those rationals.
Oh yeah, I think he is using the 3 blue 1 brown stuff.
A good,
keyed
though
differently.
mildly annoying exercise is to show that the result of adding 2 cuts gives us a new cut.
You mean the
multiplication-
Mannion library?
Yeah, this is Manum, yeah.
It's like a different kind of color palette though, so I like that part of it.
Yeah,
Yeah.
it's on the blackboard, but
Yeah.
not black.
Yeah.
Like 3 blue 1. It's very confusing.
I suppose you can customize it, but overall
Yeah.
it feels very similar. 3 blue, 1 brown-ish.
You can make it green. Like the forest.
Well, let's start with
I need,
multiplying
like,
positive numbers.
Reggie's emotes that
and
she has
by-
on her stream.
I just
Sorry, I'm
googled
getting... No, that's not...
transparent. Oh, sorry.
yeah. They look good. I empathize.
Anyway.
Okay.
Positive numbers, I just mean cuts that contain some rationals greater than 0. To multiply them, we multiply together every pair of positive rationals in our 2 cuts and take everything to the left of that. You can then write down rules for handling a negative times a positive and a negative times a negative. And at this point, a good analysis student is itching to show that this process of multiplication gives us a new cut and that the rational numbers still behave the way we want. And there are a zillion other things to check at this point. And while it is tedious, I hope the general idea is clear. These cuts behave just like you'd expect real numbers to behave, and they behave exactly as rationals already do behave. So we've constructed an ordered field that contains things that behave just like rationals, but they include these other things as well, which we're calling holes in Q, otherwise known as irrational numbers. But before we declare victory,
Good movie.
we should ask, does this new set have the least upper bound property? That is the whole reason
That's
we're
exactly
here
what I
today.
was thinking.
Recall that this property says that if we take a non-empty set of these elements that has some upper bound, then there must be a least upper bound, though possibly not in our original set. So for instance, in Q, the numbers strictly less than 1 have a least upper bound of 1. But the whole problem with the
I've never
rationals
seen that
is that
before.
sets like this one
Love
don't
it.
have a least upper bound.
Love-
But it's actually really easy to take the least upper bound
Best
of a
part.
set of cuts. Just take the union of all those cuts and you get a new cut that by definition
Whoop.
contains
Yeah.
as subsets all the other cuts. It's not tough to show that if your initial set of cuts is non-empty and bounded above, then the result of this procedure is a new cut that is actually the least upper bound. I love this construction because the final step
Another
seems simple once
exercise.
everything is set up right, but historically, it took mathematicians a long time to get all this organized and straightened out. Okay, you want the basic idea behind the proof? First, it's a straightforward argument that when you union together a non-empty set of cuts, you in fact get a cut, unless you end up with all of Q. Since there's an upper bound to all these cuts, that means there's a rational number that is not in any of them, so our union can't be all of Q. Now we have to argue that this new cut is in fact an upper bound, but that's simple since it contains every one of those cuts as a subset. And that's what it means for one cut to be greater than or equal to another. And finally, to show it's the least upper bound, imagine you took a smaller cut. Then it would be missing some rational number that was in the union, but that means it's absent from all of the C sub alphas, so it's not an upper bound at all. Now, what if we want to take the 7th root of 13? We can just look at all the positive rationals whose 7th power is less than 13 and take the least upper bound. And instead of least upper bound, we write sup, which stands for supremum. This does leave the question as to whether this really works. We know there is definitely a least upper bound of this set, but does this number raised to the 7th power actually give us 13? Well, it does, but the proof takes a little work, and I've already been talking a long time, so we'll put it in a separate video. The important thing to remember is that we can construct the reals in a fairly intuitive way from the rationals, and they have the least upper bound property. The rationals can be constructed from the integers, and they form an ordered field. And the integers can be constructed from the positive integers, just like Nick promised. And
Good job,
yeah,
Nick.
I do once again believe in the number 0. Now some quick bonus material. When I took complex analysis, we learned how to compute some really tough-looking integrals on the regular old real numbers, but we used complex analysis to do so. I started to wonder, what if I don't believe in imaginary numbers? Is the argument still valid? Is the answer still pi over 2? I quickly realized that if I didn't believe in the imaginary or complex numbers, I could fudge it. I could construct the complex numbers. It's worth taking a moment to think about how you would do this. What's interesting is that this might be the simplest construction in this whole video. We can use ordered pairs of reals to represent complex numbers. We can then define addition in the obvious way, and define multiplication in a not so obvious way, but it corresponds to the rules you already knew for complex numbers. You'll want to check that numbers of the form x, 0 still multiply and add like real numbers, and you'll have to check to verify about 100 other properties. And that's really all there is to it. You don't need to believe much of anything to solve that integral, even if you have to use imaginary numbers. Thanks for watching, and we hope we've
Baby
made
Yoda.
Dedekind cuts and the construction
that's what
of
I
number
wanted.
systems more
Yeah.
intuitive.
And complex
Nick
numbers.
really wanted to be here to thank you himself, but he is in my closet computing the decimal expansion of
Oh,
the
thank
7th
God. I
root
thought
of
Nick was
13,
dead.
and I may have locked the door from the
I
outside.
thought he was about to drop.
I told
wish
him he
Nick
could
was
come out
still
when the
around.
digits start repeating. As an aside, he's a super smart guy, but he takes forever with the simplest arithmetic assignments like this one. Anyway, if you've enjoyed even a single moment of this video or any of my t-shirts, please click like and subscribe. It really helps us out. I'd like to thank Grant Sanderson and 3 Blue 1
It's a cool
Brands
logo.
for hosting this contest and for single-handedly making math videos cool. We'll see you next time.
I thought it was pretty good.
Yeah.
I think my main criticism of it, I guess, would depend a little bit on who is the audience.
Yeah.
Because I think if it's for a broad audience, just taking a moment even to like talk about like what is an equivalence class a little longer, maybe. But if you were to drop this in as like, I'm teaching intro real analysis, and here's a video constructing all these numbers, like maybe right after they went over what a relation is and what an equivalence class is, it would fit right in. So yeah, undergraduate. So maybe it's fine for that. Oh yeah, I wrote we should start the review off with it
I
isn't
think-
easy being green, but you,
Let me
sir,
finish.
pull it off.
But my first impression of the video is that it is very dense. Even though it is called Dedekind's Cut Explained, it outlines the entire project of constructing all the familiar numbers. So it's very dense. And I have the same opinion with Leo that, like, what kind of background do you assume?
Yeah,
audience
yeah.
have? Okay, I mean, the technical content is great, is awesome, but it really feels like a book length subject, but because it really is. There's a book called Number System or something like that, called The Foundation of Analysis by Edmund Landau on this topic. It started from literally nothing, almost nothing, and all the way to complex number, and verified all the quote unquote tedious exercises in that entire book. So this is a 22 minutes video, right? So that's pretty much the entire outline. And
I mean, I think you.
and also,
Hmm.
it's so difficult to squeeze in these little extra background because this topic is so huge.
Mm.
What else can I say? For example, what do we mean by saying the newly constructed object behave the way we do? Like, who are you talking to when you say that? Right? Do you say, for example, I would probably list, this is the axioms. Okay, this is the complete ordered field axioms, and this is quote unquote our wish list, so to say. We expect the real numbers to behave this way, and then here's a concrete example of it, namely the Dedekind cut. It's difficult to verify all of. I mean, it's not too difficult to verify all of this, but it's very time consuming. So that's kind of the gist, I suppose. But it's good, very good effort, though. It's definitely very better than average, much better than average, I would say.
Well, Don, you hadn't seen Dedekind cuts before. What do you think?
Well, to be honest, this is just like too chaotic for me to actually like learn them. I'd have to sit down and watch the video a few times to actually understand them.
Yeah.
But I feel like I have an idea of the intuition now. Like it has to do with least upper bounds in construct and
Yes, you need to. It feels like you
same.
need to pause every 5 seconds.
I see.
yeah. But
Yeah.
like I don't think YouTube like can anyone teach you Dedekind cuts in 22 minutes? Like I don't think that's a problem with the video. I think it's just
I think it's.
communicating a hard
I also
topic
think
as
it's
best you
okay
can.
to
Yeah.
have a video that you have to pause and rewatch a bunch of times to get it. That's not
Yeah.
necessarily a problem with it. Here's my worry. What my worry is
Yeah,
a concept
guess
that I
it's
feel like I
just a
thought
matter
of.
expectation setting.
Yeah. Well, my worry is, and I feel like I felt this with some of the early videos I made, which is making a video for, when you're thinking of your audience, I think sometimes you can make a video for no one, meaning that the people who know what an equivalence class is have taken intro real analysis and they know this construction. And the people who don't know what a Dedekind cut is also don't know what an equivalence class is. So you don't want something where it's kind of halfway like that, where you don't include some things that, like, if you knew this, you would know the rest of the video, but you do include things that still have some like prereqs that are not included in the video. So basically, this is just me saying like you should talk a little bit more about what an equivalence class and a relation is, or if you're going to do this video. But I thought it was pretty good. Maybe it could have used another thing is like could have used a couple more analogies. The funny thing is it's not the full thrust of the video, but one of my longer videos I'm literally going to do NZQRC, but also one more thing after C, which guess in the comments what comes after C. It's not the Octonians or Hamiltonians, but in that video, at least in my draft script right now, there's like a lot of physical analogies.
I stopped believing real numbers, but I initially thought this is some kind of Norman Wahlberger style video, if you know what I'm talking about.
Oh yeah, I see. I would put it better than most. Yeah.
Clearly, there's no objection to real numbers.
Well, Reggie, what did you think about the video? Or is she locked in? I think she's talking on stream, but we can't hear her.
Can you guys hear me?
Now we can.
Yeah.
Okay.
Oh, I can't hear her. Yes,
So-
now we can.
Okay, I was gonna say that you made the comment about how if someone like didn't know, I know what a field and an ordered field and equivalency classes are, but I've never heard of a Dedekind cut in my whole life.
Yeah.
So this was new.
Okay.
me, but it was good.
Okay.
I kind of joined halfway through, so
Yeah, typical real introduction to real analysis courses skip that. Even in Baby Rudin, it is considered the appendix to chapter 1, and not all instructors covers it, as far as I
I
know.
see.
You often the case, you just introduce the real numbers axiomatically, without talking about the underlying models.
Yeah, interesting. But I should go eat dinner. Don is being meaner than I would be, but I guess I'm bad cop and good cop. So
Wait, you would go higher this time.
I don't know. I'm not even thinking about the numbers. I just see the words, and I feel like I see this and I see it better than most. Is what I see.
Yeah, I agree. I
All right.
mean, having not watched anything else, but it I don't know, it seems better.
I
Yeah,
thought
yeah.
this is a discrete random variable. I didn't know it's the continuous scale.
Oh,
Oh yeah. I mean, it's still
I
discrete.
thought
Just
the same
there's a
thing.
lot of them.
I see. Well, Don said in the future we can go into his account and change all the ratings.
Yeah, you could mess with everything if you wanted to.
Just like roll a dice and see everything 1 to 6. But anyways,
Okay.
see
I
you
think
guys.
7 is
It was
fair.
fun. Maybe I'll pop in for another one at some time.
All right. See you, Leo.
Bye.
bye.
See you, Leo.
Yeah, feel free to like come and go as you guys want. Don't feel like you need to like stay here for the entire time. I'm going for another like 2.5 hours or so.
Okay,
Guess we'll send
cool.
this.
I'll stay
Another
for
2.5 hours.
a little
Wow.
bit longer.
Okay. Say them smart. That's the job of the YouTube videos. Solving probability problems by drawing pictures. Okay. High school and undergrad.
Wait, are we rehearsing for our actual 29th stream or something?
Oh, no, this is just my... So I just have 2 shifts. So this was gonna be my actual shift, and then we added one on for, like, the YouTubers day. But you guys, like, anyone
Oh,
can
I
just, like,
see.
join in. So it's not, like, a hard and fast thing.
Okay.
Cool.
Oh, you're right. This is a repeat from the stream that came just before mine, so we're gonna skip this one. It is a cool one, though. Let me drop the link in case someone wants to
Here's
see
a
it.
tough problem.
Oops, sorry for volume. Is there a scheduled, not a publicly posted one, Max? I probably, it's still in the works. Some days are, but I should probably ask if we can post these parts of the schedule.
In the comment box it says constructive feedback.
Oh, yeah. I mean, I hope people aren't being mean if they're taking the time to do this judging thing, but
Does it allow for
Yeah, that would be crazy.
non-constructive feedback? Can we refuse to use axiom of choice?
okay, I don't think we've done this one. This thumbnail is crazy. Oh my god.
Yeah, I'm really curious about this.
Fair coins are mathematically rigged to ruin your life. 15 minutes. We post the links. So high floors in central. Why can't I pin? Okay, I can't pin the link anymore. I don't know why. Oh well. Alright, are we good if I start it?
Yeah.
Okay.
You and your arch
Yes.
rival Jimmy have been climbing these staircases for a long time. A coin is flipped once every second. If it's heads, Jimmy goes up. If it's tails, you take a step. After a crisp 1,200,000 flips, you're on step 599,998, and your arch rival Jimmy is on step 600,002. Now this seems fair. You're basically tied, with your difference in steps being just a few coin flips apart, which is exactly what you'd expect from a fair coin. However, when you really sat down to analyze who is winning second by second for the entire million plus flips, you'd expect something like this, with you and Jimmy constantly trading the lead, crossing back and forth over each other's altitude, because again, this is a fair coin. However, here's what actually happened. For a solid 590,000 of those 599,998 steps you took, you were behind, staring up at your rival Jimmy's shoes. And this isn't because you're worse at flipping a coin. No. As much as you'd like to suspect Jimmy of being a good-for-nothing cheat, that's not the case. This is exactly how a fair coin behaves most of the time. And by the end of this video, you're never gonna trust a 50-50 again. See,
Like Law and Order.
here's the assumption
Well,
most
I'm
make
hooked.
wrong,
I'm definitely
including
hooked.
me before
Yeah,
I
This is
researched this
gonna be a
video.
great one, I feel.
Over a long fair game, fair meaning a purely luck-based 50-50 game, the amount of time you spend in the lead should cluster around 50% of the time. Sometimes a little more, sometimes less, but overall it should look like a bell curve. However, the actual shape of the distribution looks like this. Really take a look at this shape. It's high on the edges and low in the middle, revealing that the outcome that feels the most fair, with you trading the lead 50% of the time, is mathematically the single least likely thing to happen.
Yeah,
So
this is a
let's
random
find out
walk.
why, starting
think.
small. Here's 4 coin flips. Each path here is one possible run of 4 coin flips. There are exactly 16 of them. Statisticians call each of these a random walk, a path where every single step is determined entirely by chance, moving up or down by 1 unit with no memory of what happened before. Let's color each path by how much of the walk it's spent above 0. If it's mostly ahead, we'll go orange, mostly behind blue, and a perfectly even split of 2 steps ahead and 2 steps behind will be gray. If we count them up, the gray bar, our fair 50-50 bar, is the smallest one on the chart. Even at just 4 flips, we see evenness to be the most improbable outcome. And if we scale this up to, say, 600,000 flips, that gray bar basically vanishes. So what does this mean? This means that you and Jimmy will never be friends. Either he'll be looking down on you, or you'll be looking down on him. This raises the real question. Why does a perfectly fair coin so aggressively
Wait,
avoid
is
the
stream
middle?
stuck?
Oh, what's up? Wait, Ming, did you ask for a pause or am I hearing things?
I heard something.
Okay. No, I don't know string theory central.
I think he is trying to get to the so-called arcsine law in Brownian motion.
Yeah. I've seen the arcsine distribution in a different context. That's what it seems like. Okay.
Let's start with an intuitive version. Imagine the walk has drifted up to plus 10, meaning heads is in the lead by 10 steps. To get back to a tie at 0, you don't just need a couple of lucky tails. You need the tails from here on out to outnumber the heads by exactly 10, however many flips that takes. And that's not impossible. A fair coin will eventually erase any lead, given enough time. But eventually is doing a lot of work in that sentence. The further you drift out, the more flips have already piled up on the leader's side, which means the more flips it now takes, on average, to claw all the way back. Every individual coin flip is still a strict 50-50, but because the leader is already several steps away from 0, a single tail towards you doesn't tie the game. It just changes the lead from 10 to 9, leaving them safely ahead. There's a vast ocean of positive numbers the walk can wander into from here, and only one narrow path back to 0. To see why, look at where the lead lands 100 flips down the road. After 100 new flips, a fair walk spreads out with a standard deviation of about 10 steps. Because Jimmy starts with a plus 10 head start, you don't need a fair split. You need to beat the average by at least 5 heads just to force a tie. And if you sum up those binomial probabilities, 82% of the time, 100 flips later, Jimmy is still in front. Leads are sticky. Not because Jimmy is cheating, but because reversing a lead gets way harder the longer that lead is survived. This isn't a new realization. Mathematicians have known this since the 1880s through a concept called the reflection principle. Imagine any random walk path that starts above 0 at some point, plus 3, and eventually ends up at some positive finish line, k. If that path happens to dip down and touch 0 somewhere in the middle, watch what happens if we take every step before that first touch point and literally flip it upside down across the 0 line. That one mirror image move creates a perfect one-to-one pairing. For every path that touches 0, there is a corresponding path that ends at the very same place, but started on the other side of the line. Thinking about the problem this way is really strong for building our intuition. However, to fully analyze the mathematical structure, combinatorics is a straightforward path. To be tied with Jimmy after 2n flips, you need exactly n heads and n tails. The numerator, 2n choose n, counts every single path that lands on an even split, while the denominator, 2 to the power of 2n, which simplifies to 4 to the n, is just every possible coin flip sequence that could happen. Dividing the two gives us u sub 2n. At 2 flips, the odds of a tie are a coin toss, 50%. But by 100 flips, that probability plummets to under 8%. By 1,000,000 flips, it's a fraction of a percent. Once a lead is established, that same fair coin will put in the work to preserve it. To find the pattern in all this jazz, let's not simulate just one flip. Let's simulate 10,000. Here, plotted on the x-axis, is the percentage of time you spend ahead of Jimmy. The y-axis represents the frequency of each percentage. As we run more and more simulations, watch the middle of the graph. As more and more simulated flips pile up, the center empties out. Almost none of these 10,000 fair, identical, equally matched rivalries end up looking even for most of their run. The middle is an effective ghost town, and the edges are the bustling cities where the fair coins actually live. But what actually is this mystery shape? Let's go back to that tie formula from earlier, the odds of a walk being back at 0 after 2n steps. According to Feller's theorem, the probability that a walk spends exactly 2k of its 2n steps on the positive side is just that same tie formula applied twice, once to a walk of length 2k, written as u sub 2k, and once to a walk of length 2n minus 2k, written as u sub 2n minus 2k, multiplied together. Now watch a random walk, and you'll see it's not really one continuous thing. Rather, it's a series of excursions, chunks that are entirely above 0, then below, then entirely above again. The reason the tie formula shows up twice is that each of these chunks basically behaves like its own smaller, independent random walk, and the tie formula counts how many ways a walk of given length can behave and land back on an even split. Here is the algebraic generating function that factors this cleanly. The tie probabilities summed up as a power series factor into two pieces. One, tracking time spent below 0, and one, tracking time spent above. They multiply because the walk is free to alternate between the two however it wants. Now let's turn that theorem into a...
Wait,
Yeah,
why is
so
one...
guys, I had to
Oh, yeah.
go.
Oh, okay.
My apologies. I wish I could stay a little bit longer. I just actually posted a community post on YouTube, say come and have fun with us, but I have to leave right now. It's a personal emergency. All right.
No worries.
Thanks
Thank you for being
everyone.
here.
It has been a great fun.
Yeah, see ya.
I'll finish out this video.
Okay. I was pausing the video anyway. I'm wondering in the middle, it says both merely mediocre here.
Yeah, one falls, the other is its mirror.
It's a strange
don't
choice
know.
of words. Okay.
Yeah. Yeah, true.
I know. I guess we'll see.
Yeah, we can continue.
Okay.
Alternate between the two however it wants. Now let's turn that theorem into a curve. Take the formula. The probability of a 2k split equals u sub 2k times u sub 2n minus 2k. Each of those u's has a clean approximation using Stirling's approximation, which says u sub 2m is roughly 1 over the square root of pi times m. Plug that in for both halves and you get a probability of approximately 1 over pi times the square root of k times n minus k. Let x equal k over n, which is the fraction of time spent in the lead. Then k times n minus k becomes n squared times x times 1 minus x. Substitute that in and divide out by how finely we're slicing up the x-axis, and everything collapses to exactly the formula we saw earlier. F of x equals 1 over pi times the square root of x times 1 minus x. This is the arcsine law. It says
It is
the
arcsine.
probability of spending some fraction of the time in the lead is neither flat nor bell-shaped. It's rather a U-shaped curve that blows up towards infinity right at 0% and right at 100%, hitting its lowest point exactly at the 50-50 mark that everyone would assume to be the fair and typical outcome. And now for the last question. Why is it called the arcsine law? The density function itself doesn't have an arcsign anywhere in it, but if we integrate it, it does. Let's take the integral of this density from 0 to x. Substitute t equals sine squared of theta. The square roots on top and bottom will cancel out almost perfectly, and the whole integral collapses down to just 2 over pi times d theta. Run the limits through and you get the cumulative probability. If you want to know the odds that Jimmy stays ahead of you for, say, 80% of the stairs or less, that probability is exactly 2 over pi times the arcsine of the square root of 0.8. The formula is called the arcsine law because its antiderivative is an arcsine function. Anyway, here's why any of this should matter to you. That staircase from the beginning of the video, that wasn't a hypothetical. It was an analogy for your favorite basketball team and Jimmy's favorite team playing a single head-to-head game. They are arch rivals with identical skill levels and talent on the floor. Every single possession of the game is essentially a coin flip. If the coin is fair, and it is, and the teams really are evenly matched, which they are, you would expect over a long enough game for the lead to trade back and forth constantly. But that's not what fair actually looks like. What fair actually looks like is that one team gets a small early lead on the scoreboard purely by chance, and then, through no fault or merit of either side, with zero skill difference at all, that lead becomes extremely hard to unwind. It's not impossible, it's just statistically improbable to reverse. So let's talk about Jimmy's favorite basketball team. It's not that your good-for-nothing rival Jimmy roots for a better lineup than you. Nor is it that his players worked harder or got luckier in any meaningful or significant way, or that your team did anything wrong. Somewhere within the first quarter, a coin landed his way slightly more than yours. A few random baskets went in, and a coin that lands your way slightly more than someone else's, even on a perfectly fair coin, is statistically almost always enough to define who is ahead for nearly the rest of the game. This explains why the real world looks the way it does. Take those basketball teams, or take two tech startups with the exact same funding and talent. You'd think that they'd trade success back and forth, but expand that out to anything. They don't trade championships back and forth year after year. One pulls away and dominates a decade, not because they're better, but because it's demanded by the math. None of this needs to be rigged, it just needs to be fair. But hey, if you're currently stuck on the losing side of a streak, remember that the math does swing both ways. A fair coin eventually gives everyone their moment in the sun, even if it takes a million flips to get there. Anyway, that's the arcsine law. Next time you're on the losing side of a cumulative coin flip competition for the 600,000th round, don't blame Jimmy. Blame nobody. Thanks for watching.
like that. That was cool.
Yeah, I really love the art
I
style.
really, yeah, and it was. I actually never heard of the art sign law before, or if I have, I don't remember. Um, so yeah,
Yeah, I
I
encountered it
really liked it.
once during a PDE's class, and I was so
I
confused
see.
because like they didn't tell us what the distribution would be, and I thought I was wrong, so I got the arcsine law. But no.
Right.
Um.
Interesting. No, that was cool. I think the audio was too low,
Oh,
but
really? Okay.
well, it was
Maybe I
really
need.
quiet on my end, and then also in my stream they were saying it sounded just very quiet.
Okay.
Yes.
That might
But
just be
is that
working
what
with
they're even
Discord
looking
too.
for? Yeah, like
Uh,
um
I probably care more about like the math content.
yeah, figured. Okay. That makes sense.
Create visuals and art. But it's like sound is really, or that. I mean, his mic definitely could have been better, but
It's not really what they're concerned with,
yeah.
probably.
Create visuals and art. I wasn't like towards the end of the video with giving examples like the basketball game. Like, I sort of get what he's going for, I think, but that's not as easy as a 50-50 coin flip. I feel like
Right, yeah, it's not necessarily parallel
yeah,
comparison.
it
Yeah.
it is a nice like perspective though for why even things that seem even don't always have even outcomes. But yeah, I don't know if those examples were like my favorite.
Yeah, true. Yeah, I think up until that point, the explanation was really good.
Yeah.
Wait, but did it say that what was the audience? It wasn't high school, right?
Oh, high school, undergrad, and grad, so all over the place.
High school's I don't to me, high school audience for that is crazy, but I don't know if I'm getting nitpicky. I mean, like I thought it was well explained though.
Yeah, because we had some integrals and derivatives in here that I wouldn't consider high school for sure, and even then, like
Yeah.
Stirling approximation, yeah,
Mhm.
that
Mhm.
high school's a little generous, but
Whatever. Yeah.
hmm. Yeah, and so like say stuff in my chat is saying like it's really good from a storytelling point of view.
Yeah, the narrative is strong.
Yeah. Unless they're a math Olympiad, well, yeah, that's true. um, I feel I like to see like just a tad more than the last one, and if I give the last one a 7, I want to
Yes,
give this one a seven
I
and a
agree.
half. Okay.
Yeah, I was gonna say the same thing. Yeah.
Hmm. Uh, the standout features from this video for me are the storytelling and the visuals.
Yeah.
The well, actually, okay, storytelling, visuals, and the subtle humor. Maybe that's a part of the storytelling in the visuals,
Right.
but I don't
Yeah.
know. I'll throw it in.
Yeah.
Yeah, and so I guess Quitch Math is saying like the details are dense. To be honest, I did kind of glaze over a lot of the actual hard details in the middle part of the
Same.
video. Okay, wasn't just me. I'm
Yeah,
glad.
no, I'm like, okay, I understand the narrative and what's going on, but yeah,
So
it
actually,
did lose me a little bit.
okay, that's worth mentioning them for sure. Were somewhat difficult. It's been difficult to follow. I like the spirit of the examples given at the end of their processes, but those real world examples are a little too complicated to be represented
Yeah,
by coin flips.
yeah, for sure.
Okay. I do, however, like the I guess like I don't know, philosophical or life message.
I was gonna say something about real world applicability. I don't know. Yeah,
Even the fair process can have, I guess, maybe seemingly
yeah,
unfair outcomes.
Right.
Hmm.
How much do you have to write for the feedback, or is there even is there a
There's no minimum. We're capped at, I guess, 10,000 characters.
10,000?
Okay, yeah.
Yeah.
So we need to, like, I think I was just wondering, like, this is probably good enough. I don't know if I have any other thoughts.
Right. I don't either. I think, yeah, I think that about covers it. I mean, I think it was really good overall.
Yeah, at first I was wondering if it was like if the art was going to be bad, but not on purpose. Like, especially at this in the opening.
Yeah.
But I realized it was
Right.
like it's just a
It's
stylistic
self-aware.
choice. Yeah, exactly.
Yeah.
So that
Yeah, I like that.
yeah.
That's cool.
All
Okay,
right, I
I'm
guess I'll
gonna
send this.
go.
Sounds good.
Yeah, I think you should send it. Thank you for letting me join. This is cool. I guess I'll be back doing this soon.
Oh yeah, like 29th or something.
Yeah, 29th it seems.
Yeah, thank you for helping
We're
on like
reconvening.
a moment's notice and having to adjust your OBS and stuff.
Yeah.
I know it's annoying.
No, oh no, yeah, it's okay. It was a good lesson for me to learn. I'm becoming more less technically challenged,
That's
technologically
good.
challenged every time. Okay, cool.
All right.
Well, I'll talk to you later then.
Sounds good. See ya.
Bye.
Bye. Okay. That was Sigma Reggie. She's streaming at this moment, so she's awesome. Please go over and follow her. I guess we're gonna have a Magic Squares one here. So I feel like I should say let me catch up with chat here. You still barely know what a generating function is? They're really cool. I've learned a little bit about them for probability stuff. Arad says, I think high school get the intuition without getting all the details. That's fair, Arad. I think I agree with that. I also think there's value in math expo videos that appeal to high school students and drop a bunch of things that they might go Google. Yeah, that's another fair thing, Floppy. Some European high schools where this would be on par, probably not American high school. Okay, I wouldn't know. Not good math exposition. They're good, like, math name thing about find out about. Yeah, you find out about left numbers from Vsauce. Fair enough. Oh. Okay, so Leo A, as soon as you left, I guess I'm too lame to keep people in the call, but it was really good. I really liked it. It's about random walks. I if you have a spare for 14 minutes sometime, I would highly recommend it. But both me and Reggie liked it more than the one that we all watched. And you are being asked what comes after C. Floppy's been desperate. Are you saying NBA teams, so they're flipping coins against each other? I mean, no, I was about to say that they do coin flips for like football, right? I don't think they do for basketball though. Keep trying to hit on red, one day you'll win. That's true. Independence is not real, everything life is predetermined, just give up. Just give up. I'm not a mathematician, the condo's above my level. Part was probably incorrect because it assumes the lead in the game decomposes in smaller steps that are independent. Yeah. Okay. D. True. Okay, Leo's giving a hint to Floppy. It's the destination for algebraic geometry. Classical algebraic geometry. Whatever that is. Okay. The secrets of the magic square of squares. High school, middle school, magic squares of squares. A 20-minute video documenting my year-long attempt to find a magic square of square. I don't know what this means. Little knowledge required, but it is fast-paced. Has some interesting simple math for those that are curious. A magic square is basically a Sudoku, right? Or is that no? That's a Latin square. What's a magic square? Or are they the same thing? Should I Google it or should I let the video explain it? I'm gonna Google it. It is Sudoku? Okay. What's the difference? What's a Latin square then? Oh wait, this is diagonals. Do Sudokus do diagonals? I don't think it does diagonals. It's almost a Sudoku, but not quite. It doesn't have the sub-squares, and it does do diagonals. I probably should let the video explain it. I do want to know what a Latin square is. Okay. Anyway. Oh, maybe Fembox, yeah. Today. Larry Lobster? We're gonna have Larry Lobster teach us about magic squares. Oh, come on. I wanted the profile pic of Larry Lobster. Okay, am I allowed to pin things now, Twitch? Oh, I forgot. I meant to do this before starting the video, and I haven't started the video yet. I have recently met a shitload of people who stream math on YouTube who I didn't know existed, and I feel like I should pass along their usernames to people on the Twitch side of things, because I just never knew that there were this many people who streamed over on the YouTubes. That's my list currently. Exactly, Leo. I had to like dilute you a little bit. There are Max. What's the right type of object you should be thinking about? Is it a field? I don't know. I'm sure someone in chat knows. No worries, Fembox. On the 29th of August, so the Saturday after next, there's going to be a YouTube Mega Review-a-Thon day. It's not a ring. Okay. It's a square. So yeah, we were on the call with Math with Ming and Leo Lectures out of that list, and then Sigma Reggie, who I already shouted out a little bit earlier. Now I'm back to being solo though. The links are broken. Oh, you're right, because YouTube truncates things. Wait, do they? They do. That's so annoying. Yeah, let me... Wait, what the heck just happened? Okay. I think those are fine. Save time when writing function from the domain D to reals, just say 32. FDR! Oh my god, syntax. Ming, it's going great. The video we just watched, I think you... Well, A, I hope things are okay with you. And that things are good. I already said that. The video that we just watched before this... Not that. About random walks, it was really good. It has a very nice payoff, I think. So both me and Reggie liked it more than the video we watched before. So yeah, we're about to do this one about magic squares, which I think are slightly different than Latin squares. Okay, I think we're ready to get started on this. Yeah, I don't think he ever said brownie motion in particular, but it's the same thing, I think.
Today, we're learning about magic square of squares. So we know squares, be there or yard one, so they're a bit bland. Well, if we could make things a tad more, dare I say, magical? Let's take a square and turn it into a 3x3 grid, so there are 9 total spots, labeled S1 through S9. Now, we can fill each spot with a different positive whole number, no matter the size. But the sum of each row, column, and diagonal must be the exact same quote-unquote magic number. If we do that, then we just made a 3 by 3 magic square. But I mean, wouldn't that be kind of crazy? Look at all these equations that we need to satisfy all at once. I mean, is something this magical even possible? Oh, so it turns out I might have been exaggerating a little bit. Making 3 by 3 magic square isn't all that difficult, especially if you know the trick involving the middle number. If we do some algebra, adding some of the equations with the middle number together and subtracting some without it, simplifying leaves us with a kind of crazy result. The magic number is exactly 3 times the middle number. Let's just call that S from now on. Since all of the numbers in our magic square have to be different, we know that all numbers have to be some distance, d, away from S. So in the middle column, we could say the top spot is S plus d1, but since the whole column needs to sum to 3S, we know for a fact that the bottom spot has to be S minus d1. A similar argument holds for any sum going through the middle. Now we have an interesting byproduct. For sums not going through the middle, we still need to sum to 3S. This leaves one option. D3 equals D1 plus D2, and D4 equals D2 plus D3. Doing some algebra, we can say D4 equals D1 plus 2D2. So this whole magic square thing can be reduced to picking an S, D1, and D2. We just have to be a little careful not to pick too high of a D1 or D2 so no spots go into the negative. But besides that, it's kind of trivial. I guess this is why magicians don't reveal the tricks, huh? But what if we could spice things up? So these are squares with whole number sides, and these are square numbers, the area of said squares. But what if, instead of filling our magic square with just any whole number, we restrict ourselves to square numbers? That way, it would be a magic square of squares. Alright, if we call the larger square in a row, column, diagonal m squared, and the smaller square k squared, then it will look like this. Let's take a closer look at the middle column. See, we need a number S such that its square is equal distance to two other squares. Thinking about that more visually, we can have 3 actual squares besides k, s, and m in areas k squared, s squared, and m squared. If we cover s squared by the area d, we're left with k squared. And if we add d to s squared, we get m squared. Another way to visualize this is by putting k squared in the center of s squared. Notice we have 90-degree rotational symmetry, meaning if we rotate 90 degrees, it looks the same. It's important that what we're about to do keeps that symmetry. Now let's add 4 triangles. Each triangle having 2 points at adjacent corners of s squared and 1 point on k squared. Notice we can spin k squared all around and the triangles follow. K squared can actually be really close to the size of s squared. It might poke out when we spin around, but what we really care about is when everything lines up like this. Since k squared is a square, all of its angles are 90 degrees, meaning this angle is also 90 degrees, which means this triangle and all other triangles are right triangle. Zooming back out also reveals that the triangles take up all the area between s squared and k squared, meaning it has an area equal to d. Flipping the triangles adds d to s squared, creating another square which must be our m squared. So now we know that the legs of a right triangle add to get the sides of m squared, it equals m, and the difference of
So I gotta be honest, the visuals were really cool just then when he was rotating the square around. I don't know what the triangles mean. He just said, let's add in some triangles, but I don't know, like, why. The visuals are really amazing, though, so far. I know, I guess I'll just keep on going.
The legs get the size of k squared is equal to k. Now we don't know much about the legs of the right triangle yet, but what we do know is that m and k are whole numbers. You can say that the partial part, p, or decimal part, or any part less than 1 is 0, because they're whole numbers. So L1 and L2 partial parts need to either add to get 1, or they add to get 0 for m to equal L1 plus L2. Similarly, the difference between L1 and L2's partial parts must be 0 for L1 minus L2 to equal k. This allows us to do some algebra and ultimately say that L1 and L2's partial parts are either both 0 or they're both 1/2. However, S is also part of this triangle as the hypotenuse. Therefore, we can let the partial part equal 1/2 and then apply the Pythagorean formula. W here represents the whole part of L1 and L2. All this to show that if the partial part of L1 and L2 is 1/2, then we're left with a whole number plus 1/2 equaling a whole number, which is not how math works. So we know the partial part cannot be 1/2. Therefore, it must be 0. Therefore, we know all sides must be whole numbers. So all this hooping and hollering is to say that if we find a right triangle with whole number sides, then we know a variable S is the hypotenuse, D is 4 times the area of the triangle, K is the difference between the legs, and M is the sum of the legs. Now the next question might be, how hard is it to make these right triangles with whole number sides, also known as Pythagorean triangles? Well, luckily for us, it's super easy, hardly an inconvenience, because of our old friend Euclid and his amazing formula. Giving 3 whole numbers, we can make a Pythagorean triangle using these formulas. The only slight caveat is in the formula for L1. If b is larger or equal to a, we have a negative length. So we can just say, let a be the larger of the 2 numbers. So what are we waiting for? Let's put this to use. Here, we're going through some examples using different a's and b's. Changing z essentially just scales everything up. But we're not quite done yet. You might have noticed already, but our magic square has more than one column. It has rows and diagonals we have to worry about too. All in all, we must find an S that has at least 4 different D's, so we can make a proper magic square of squares. Visually, we need 4 different Pythagorean triangles with the same hypotenuse, but algebraically thinking, we need 4 different ways of having A, B, and Z that all make the same S. One such S is 65. Why is 65? Well, 65 is 5 times 13, which we could say is 2 squared plus 1 squared times 13, or we could say is 3 squared plus 2 squared times 5. But we could even say it's 7 squared plus 4 squared, or 8 squared plus 1 squared. The first two is a direct consequence of 65 being the product of 2 sums of squares. Essentially, we just said 65 is 5 times 13 and 13 times 5. The other 2 ways of writing it is more interesting and comes from us applying the Braha-Gupta-Fibonacci identity, which is just a fancy way of writing that the product of the sum of 2 squares as the sum of two squares in two different ways.
Is this the thing that we were talking about with Leo? Like a few... Yeah, okay. I recognized it. Yeah. Okay. Fembox recognized it too. You were there too. Oh, cool. Consider a sphere of the North Pole and 2 points on the equator that are quarter of the circumference apart, all of them connected to geodesics. Is this a triangle? That, Max? Depends on your definition of triangle, I guess. It's called retention. Thank you, Leo. Yeah, you can use complex numbers for this. Okay, anyway. I'm mostly lost with what this video is doing, by the way, but I'm plowing through it.
We can actually go on a whole rabbit hole talking about how multiplying different sums of squares yields more and more Pythagorean triangles with the same hypotenuse. But we'll move right along now, because did we low-key just solve it? I mean, 65 is an S with 4 different D's. Let's plug this bad boy into our formulas and make a 3x3 magic square of squares. And here it is. Look. This row, this column, and both diagonals all add to the same number, 3 times the middle number, and all numbers are square numbers. Let's freaking go! But alas, these columns and these rows do not add to the magic number, and that's because we forgot to make D1 plus D2 equal to D3, and D2 plus D3 equal to D4. Ugh. Let's stop looking at numbers for a second and go back to our visualization. Here is a set of A, B, and Z's with a square S and area of triangles D. Part of our problem that there are a bunch of different ways to have these numbers. In fact, they are infinite. This is an endless expanse, and it even goes in the third dimension. And that of all of the infinite possibilities, we have to hone down 4 with the same S and just hope that they have D1 plus D2 equals D3 and D2 plus D3 equals D4. That's insane. But you know what? What if we do something also a bit crazy? What if, for all these infinite squares, we scale them down by their S so they all have an area of 1? Now, at least it's obvious that Z isn't really important. We can throw that guy out. But to show how this helps us, we need to play pretend. If we pretend that these scaled down D's, which I like to call non-dimensional D's, have the special property of D1 plus D2 equals D3 and D2 plus D3 equals D4, then we can scale them all by S1 squared times S2 squared times S3 squared times S4 squared. Now every D is guaranteed to be a whole number, and the property still holds. And all the S's are still equal, meaning that if we solve it on the small scale, we can solve it on the large scale, and vice versa. So let's take a deeper look at this formula of our non-dimensional D. As noted, Z is not important. It immediately cancels out. We can expand and divide both numerator and denominator by a to the 4th, and then simplifying leaves us with this. Non-dimensional D is not dependent on A or B, especially not Z, but instead the ratio of an A and B. Since we declared A to be the larger of the two numbers, we know that this new variable is strictly between 0 and 1. Let's ignore that for now and look at the graph of this function. Starting far into the negative n, we have a small non-dimensional D values. As n increases, our non-dimensional D goes up to 1. It drops down to 0 at n equals -1. Goes to -1, then goes back up, down again, and as n goes to infinity, our non-dimensional d approaches 0. But why is non-dimensional d restricted to 1? Why can't it be any bigger? Well, since our non-dimensional d is d over s squared, for it to be larger would mean d is greater than s squared, and that would make a spot in our magic square squares going to the negative, which is illegal. Now, we only really care about a non-dimensional d. So, between -1 and 1, we go through all possible non-dimensional d's. So we don't really care about the rest of the graph. In fact, if we look at our magic squares template, you can see that d is added and subtracted. So I don't care about sign either. So we can just focus on n going from 0 to 1, where non-dimensional d goes from 0 to 1. We could continue this argument and say we only care about n going from 0 to square root 2 minus 1. But for now, we'll look at 0 to 1 because it's easier and nicer to say. Now, you might have noticed this green dot. This is what I like to call n prime. Its formula is very pretty. It is another n that shares the exact same non-dimensional d. In fact, there are 8 total that share the same absolute value of non-dimensional d. Each one is separated by these inflection points at n equals negative square root 2 minus 1, n equals -1, n equals negative square root 2 plus 1, n equals 0, n equals square root 2 minus 1, n equals 1, and n equals square root 2 plus 1. Notice how some of these inflection points have non-dimensional d as 0, which means d, the distance between the center number and other numbers, is 0, which means repeating numbers on our magic square squares, and that is also illegal. Some other spots give a non-dimensional d of 1, which would lead to a spot in our magic square squares being 0, and I guess isn't illegal, but for reasons we'll discuss a little more later, it's actually n here that is illegal. But this is even the coolest graph we can make with our non-dimensional d's. Since each non-dimensional d is dependent on one variable, we can actually graph these equations on 2 different surfaces in 3D. Take a look. One thing you might notice is this giant gaping hole in the middle. Well, that's where d3 and d4 are forced to be greater than 1. But as we discussed, that's illegal. So there are no real n3s or n4 that exist at those areas. Again, you might be thinking, we solved it! But alas, no. Because I've been lying to you slightly. These are not the actual values for n's. In fact, even if I make n1 and n2 pretty, n3 and n4 are absolutely atrocious. Even this is lying to you. These numbers go off for forever without repeating. That's because they're irrational, meaning they cannot be written as a ratio of whole numbers, which, if you recall, is exactly how we define our n's. The real culprit is how you reverse d to get n. You can see here in the formula, you have to take the square root. But taking the square root of not a square number, all you're left with is a filthy, irrational number. This is where the problem lies. We have to look for n1 and n2 that gives us rational, meaning it can be written as a ratio of 2 whole numbers, n3 and n4. I also want to note that n1 or n2 cannot equal 0 or 1. Because, as we talked about before, that will give us a magic square of squares that has repeated numbers, and that is also illegal. So this is kind of tragic. I'll give you a moment to process. Alright, we're not done with the learning. Just how we had our green dots before, even between 0 and 1, we had n and n prime. We can now do the same for each dimension. This splits our graph into 8 parts. So the sliver of the graph is a representative of all magic squares of squares. If we can't find a rational point here, then one simply does not exist. I was inspired to search into magic square squares and snatched the first portion of math for this video from the number file video featuring Aileen called the Anti-Parker Square. And then after working on this for about a year and a half, I eventually reached out to Professor Anthony Virilli Alvarado after rewatching another number file video, and he put me in contact with Daniel Flores, who was an author on the paper that proved the existence of n by n magic squares for n greater than 3, which was so cool. I was fangirling so hard, but unfortunately, he gave me some bad news. Let me show you. So us wanting 4 non-dimensional Ds, such that D1 plus D2 equals D3, and D2 plus D3 equals D4, is equivalent to us looking for 4 Pythagorean triangles that areas have the same property. And what Daniel showed me, and what hurt my pride and my ego, is that this link and this question was asked over a decade ago by this fellow named Thomas Bloch on a math forum. Even though I didn't find the magic square squares, or disprove their existence, or make any new ground on this problem, I hope by making this video, I inspire somebody like you to solve this and put an end to this problem once and for all. And maybe I'll make that sequel video to show you some of the more things I tried to try to solve this problem. But if you don't, I just appreciate you for watching this video. So, thank you.
Okay. There's a couple of things, or there's many things I love about this video. There's a couple of things that I don't love, though. Let's try and put it all together. Things I love. His personality and letting it lead into his voiceover. I only ask for even more weirdness. No, Leo not in it. I guess not letting him bleed, letting it show in his voiceover. He's also really good at reading. Because I assume this was scripted. His mic could have been better, but, like, that's not a big deal. Animations were fantastic and aesthetically mesmerizing at times. This one.
And 1 point on K-squared.
This reminds me of like it's an even more fun version of the DVD symbol bouncing around the screen.
Notice we can spin K-squared all around and
Ming gives it an 8 out of 10. I don't know. I don't think I'm going that high personally. Wigglebot says 10 out of 10. Best video I've ever seen, 2 out of 10. I love that it shows a failed attempt. It's very uncommon in YouTube to do that. I mean, on the internet. Perfect 5 out of 7. That's oh wow. That how old is that meme now? I I haven't heard that meme in a while. Things I don't love. Pretty much lost after the triangles came in around 4:30. That's my main criticism here. I really could not follow this video. He didn't explain what the triangles meant, and then he just started throwing out a bunch of equations. He didn't immediately explain the triangles mean. And I'm gonna like clean this up and make it into a paragraph or two. But I'm trying to figure out what my thoughts even are. And then as more equations got thrown around, I was left behind. What the triangles mean and what they order. I feel like I'm probably harsher on this video than most would be because this feels very much like a hobbyist math problem, and that's just not the type of math that I typically like. Like magic squares, I don't know. I just had never enjoyed putting much thought into them. I was wondering, like, even though I couldn't follow the actual math he was doing, his approach was very, like, analytic or algebraic or whatever the proper term is. He was pushing a lot of symbols around the screen, and I wonder if there's a completely different subject you can use to talk about magic squares that will be better for this. I assume not, but I feel like when you get to a certain point of having to shove symbols around a page, you usually try to switch tactics. I could be wrong, though. I despise filthy casuals, I guess so. No, that's not poor taste at all. If anything, I'm the jerk for saying I don't like hobbyist math. That's kind of a gatekeeping thing to say, so. I don't know if it's gatekeeping, but like, I don't know. I just like differential equations and calculus, basically. You don't like people or joy. Hobo math? What is hobo math? That sounds fun. Is that like the two trains leaving the station problem, but there's two hobos riding on the trains? And when can they high five? Yeah, Fembox. So I imagine that you and people like you would have enjoyed this video a lot more than me. I still enjoyed it. Just not as much, I think. I assume it's scripted, but I never noticed it in how it's being read. Calculating your head how fast you have to run to not go splat. Wait, do hobos, like, are they stuck in front of trains? I don't know hobos were like that. I really enjoyed personality and how he let it show in the voiceover. The metal thingy broke off? What metal thingy? You gotta hop. Oh, okay, yeah. Cartoon Law says you have to run away from a big thing in the same direction the thing is going. True. You can't just go to the side. What? Yeah, that's true. Oh, from your brakes? I'm not sure. I think I meant like a metal thing on my end broke off. I also love that it shows a failed attempt, which is very. I mean, it's not unique on the. Okay, maybe I should say it's very unique on YouTube. A failed attempt, and admits it. Brace. Oh, your braces that you were talking about earlier. Okay. Yeah, having issues with your braces is really annoying. I do not miss having braces, although I kind of need to get them at some point. Yeah, exactly. However, I was pretty much lost after trying to come in around 4:30. I was left behind. Not naming any names. Where's are hiding from right now, Don? Oh, there's a lot of failures I'm hiding from. I'm not hiding from failures. I stream Daisy. If I really wanted to show my failures, I'd apply to jobs on stream. Well, that'd also be like doxing myself, but also, it's like I wear braces for life now because first they put them there after normal braces to keep my teeth straight. That is kind of the scam with braces. I mean, it should be retainers you just wear at night though, but you know, you kind of say that you'll wear them, you never do. If you have actual braces on though, that's a huge scam. I'm hiding from the JE advanced questions. I will definitely admit to that. Oh no, Leo, I'm definitely failing at that too. Overall, it was still a really enjoyable video because of the upsides. Did YouTube eat your other? I think it did. What fails are hiding from better not be that. So yeah, I don't know. Do you do math Olympiads in ancient Greek? Yeah, I don't know what's worse, Olympiad or JE. I changed my YouTube title, Max, and it's unfortunate because I feel like if it just means that no one clicks on my stream now. And I guess I need to keep on playing with my YouTube title, but I changed it. It's funny too, hilarious even. Oh, really, Lucas? That's funny. As G or G? Yeah, it's an acronym. I think it's an acronym. Okay, I think we're we're not nexting. Oh wait, no, we're not. Ooh. I think other people will give it a 7. I'm at a 6 though. Am I at a 6? I think I'm at a 6. Yeah. You're 6 or even 5, you didn't see the whole thing. Okay. 7 is a 5 and mine a... Yeah, like, I really like how they're doing the scale here and how they're asking the question, but definitely if you just ask for a 1 to 10 rating, like, you know, for a fast food place or something, like, the average was more like 7. You're right. Ooh, this could be fun. Number palindromes of differing bases. Number of palindromes? I don't know. Or no, number palindromes. Okay. Oh, never mind. See how number palindromes relate to convergence of an infinite series, Pascal's triangle, and the triangular numbers. Promising a lot. Alright, see ya, Leo. Thank you for hanging out. Change the base of a set of numbers. Reveal more palindromes. There's a particular pattern for finding some palindromes. Well, you just generate the palindromes, right? Like, you can take any number and make it a palindrome, right? The sum of reciprocals of every palindrome number and every base... Well, that's very specific. Surely not. Because 1 over n doesn't converge. Well, maybe it does, if you remove things from 1 over n. I don't know. Way to make palindromes without needing numbers. Okay. Oh, this is so long. Okay, we'll just read this part and then we'll get in there. In Blender, I wonder how it's gonna look. Integers and bases b greater than or equal to 2. I guess you can have. I mean, base 1 doesn't make any sense, but I guess you have like base 1.5. 6 months of research, 40 hours of animation programming. So I really hope you enjoy. Wow, an egg. Okay, this is already visually really strong. You have trouble seeing what number like 2C looks like in base 16? Yeah, I mean, everyone does. It's just hard to get used to. If you use them a lot, though, you, they become like regular numbers to you. Dr. L, find the mistake in polar coordinate, or in polar x equals r cosine phi, partial with respect to x of r is equal to d by dx. X squared plus y squared equals x over r equals... Isn't there a square root in there? Well, it's r squared equals x squared plus y squared, right? I don't know. I feel like I'm misreading what you're saying, Dr. L. If it's not that, I'm not sure what it is. Okay. I think I already put the links in chat. Unary? I mean, how do you... If it's base 1, can't you... Doesn't it just not make sense? I don't know.
You might already be familiar with English palindromes like I, radar, and Professor Ross Eforp, but today I want to talk about number palindromes. Number palindromes, just like word palindromes, are numbers that can be read the same forwards and backwards. The date this video was recorded, June 29, 2026, is one of these special numbers, meaning I can flip these tiles around and get the same date I had before. 62926 is an example of a 5-digit base 10 palindromic number, meaning that we can rewrite it as a sum of 5 increasing powers of 10 with non-negative integer coefficients less.
Oh, like tally marks? Okay, sure. For unary. It's number 5 palindrome? I guess you could count single digits of palindromes. It might make sense to exclude them depending on what you do. Rats live on no evil star? Well, I haven't seen that one.
Than 10. Each base b can represent numbers with d digits like this. A sum of increasing powers of b to the power of I multiplied by an integer c sub I between 0 and b minus 1 that is represented at the ith position in the number, with I equals d minus 1 at the leftmost position and I equals 0 at the rightmost. The final number is written with a subscript b at the end to indicate which base it's written in. Base 10 is the base we use for majority of the math we do, but you might already be familiar with other bases like base 2 and base 16 if you're into programming. But as much as I would love to talk strictly about decimal, not at all, I want to talk about number palindromes of all bases to look for my favorite part of math.
Oh, these captions are built into the video. That's kind of interesting.
Patterns. Speaking of patterns, I want to look at one of the most well-known patterns in mathematics, Pascal's triangle for palindromes. In case you don't already know, to make Pascal's triangle, we first need to make an infinite grid of zeros. Then, we pick a starting place, let's say right here, and set it equal to 1. To make the rest of the triangle, we set each element in the next row equal to the sum of the two numbers above it. If we remove the zeros, this is how Pascal's triangle usually looks, but to make my life easier, I'm going to shift everything so that each row is aligned to the left side of the screen and not the center. Much better. And then I'm going to give each number a position based on their column number, k, and row number, n. The first thing we can do with Pascal's triangle to get palindromes is to multiply each number in a row by an integer b raised to the power of its k value. If all the numbers in the row are less than b, then that number is a valid palindromic number in base b because each row of Pascal's triangle is symmetrical down its center.
Wait, I missed that. Yeah, this is made in Blender. And I thought Blender was 3D. Maybe you can also do 2D stuff in it, though. I don't know if he pioneered it, Winklebot. He certainly popularized it, as far as I know. Can also do video editing. Wow, I didn't know it did all that. I need to hear again why palindromes. Oh, I guess, well, you can see that these are all just palindrome, because, like, Pascal's triangle is symmetric, right? Surely this misses a bunch of palindromes, though. Yeah, Dr. Ella, I'm right there with you, but apparently it does more. Okay, I need to rewatch that last, like, 10 or 15 seconds, so I backed up a bit, but let's keep on going.
Left side of the screen and not the center. Much better. And then I'm going to give each number a position based on their column number, k, and row number, n. The first thing we can do with Pascal's triangle to get palindromes is to multiply each number in a row by an integer b raised to the power of its k value. If all the numbers in the row are less than b, then that number is a valid palindromic number in base b because each row of Pascal's triangle is symmetrical down.
Oh, okay. Sorry, this is complicated. Because that's why I'm pausing here a lot. This explanation is so complicated, I think, because even if you go down one more row in Pascal's triangle, you start to get double-digit numbers. And so things get a little more complicated, I guess. Hardly know her? Yep.
Center. But what I found much more interesting about Pascal's triangle is what happens when we look at the third column in our table, a set of numbers called the triangular numbers. If we look at the table, we can see that the nth triangular number, t sub n, is equal to the sum of the first n positive integers. So t sub 1 equals 1, t sub 2 equals 1 plus 2 equals 3, and t sub 3 equals 1 plus 2 plus 3 equals 6, and so on. All of these sums are called finite arithmetic series, meaning sums of numbers that increase by a fixed value and start at a constant value, both of which are 1 for the triangular numbers. This allows us to use the formula above for calculating the sum of an arithmetic series to calculate the nth triangular number t sub n. First, we substitute t sub n for s sub n, then our initial term 1 for a sub 1, then our final term n for a sub n. Then we leave the outside n term as is. We'll come back to this formula in a second. For now, I want to look at this table representing the nth triangular number written in base b, where n is.
Ming, I think submissions are closed. I think they close sometime in June or something. But it is a public competition that anyone can enter. So I'd have to look where it is on the website. But like, it's always something you could do next year. I imagine it's too late for this year, though.
Even. If we look at the main diagonal of this table, it looks like there's a pattern of palindromes starting and ending with 1, with the center increasing. At least for bases 3 to 10, it looks like the center digit has a value of b minus 3. This pattern looks like the ith number in base b, such that I equals 2 times b minus 1, is a palindromic number in that base of the form b squared plus b minus 3 times b plus 1. For now, it looks like this pattern holds true for at least 7 bases, but if we want to see if this pattern remains in every base, we need to do some algebra. If we take our formula from before for getting t sub n and plugging n is equal to I is equal to 2 times b minus 1, we get an equation for t sub I. After a bit of simplification, we arrive at the equation for the ith triangular number, t sub I, is equal to 2b squared minus 3b plus 1. Based on the pattern we observed, t sub I should be equal to b squared plus b minus 3 times b plus 1, but if we simplify the right side of this equation, we see that both sides are actually equal. Now we know that this pattern should hold true in any base we look at, But looking back at the table, it looks like there's an outlier in the binary row. For some reason, t sub 2 in binary only has 2 digits, unlike the 3 digits that the other numbers in the diagonal have. To see why this is, we need to go back to our equation for what number should be in that cell. B squared plus b minus 3 times b plus 1. Plugging in 2 for b reveals the issue. The center digit is meant to have a negative value, but adding it all together, we still get a value of 3, which, when converted to binary, still follows the pattern of starting and ending with 1.
But I've had enough of triangles, so let's move on to something else.
Does the sum of the reciprocals of every palindromic number converge to a finite number? For a lot of people, most of that statement might not make any sense in the slightest, so let's go through it step by step. This question deals with the convergence of an infinite series, a topic typically covered in depth in Calculus 2. What it means for an infinite series to converge is that, as you add up the infinitely many terms of the series, the sum approaches a finite number rather than adding up to infinity. An example of a convergent infinite series is the sum of 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on, which can be written using a shorthand notation that I've been using throughout this whole video called sigma notation, as the sum from n equals 0 to infinity of 1 over 2 to the n. To show why a sum of an infinite amount of numbers should approach a real value rather than exploding off to infinity, we can look at the sum from a geometric point of view. If we were to make rectangles with areas that correspond to each term, then place them next to each other, we can see that as we add more rectangles, the total area seems to approach 2, or 2 full squares. With an infinite series, there are many ways to prove whether or not it converges. But before we continue, we need to take a detour to discuss how we even generate a palindromic number. Before we try to come up with a method to generate palindromes, we can just go with the simplest route and just brute force our way through a list of every single number in a base and throw out any number that isn't a palindrome. This is guaranteed to work, but it doesn't give us any information that will help us find our sum, and it requires us to check infinitely many irrelevant numbers, wasting more time the more digits we add. The better method to generate a palindromic number in base B is what I'm going to call the mirror method. To do the mirror method, we start with a number n in base B, and n prime is the reverse of n without leading 0.
Okay, I was about to be really mad if the suggestion for getting palindromic numbers was to generate every single number and throw out the bad ones. I never tried to generate a palindrome before, but that just seems like the first thing you should start with to do this mirroring thing.
Was removed. Next, we let delta be the set of all possible digits for a given base B, which we know from earlier is all integers between 0 and b minus 1 inclusive. To generate an odd digit palindrome, we take a digit c in delta and place it in between n and n prime.
Oh, I didn't think about that though. For every mirror you do, you have to insert every digit in between. Okay. Yeah, that's fair.
For an even digit palindrome, we just place c in the center twice between n and n prime. This allows us to create every single palindrome in a base, but it also allows us to know how many different palindromes there are in a given base that have x digits.
Wait, aren't you double counting though? If you're doing this part up here, you're surely double counting. Because what happens when you get to 2101? I guess you're adding more things into, well, maybe you're not. I don't know. That seems weird to me.
A base, but it also allows us to know how many different palindromes there are in a given base that have x digits. Let's say our n is a y-digit number, where y equals 4 and b equals 3 for this example. The first digit cannot be 0, so it must be an integer between 1 and b minus 1 inclusive, leaving b minus 1 options for the leading digit. Then, the following y minus 1 digits can assume any value that is an integer between 0 and b minus 1 inclusive, leaving b options for the remaining digits. We can then use this information to calculate that, given y digits, there are b minus 1 times b to the y minus 1 possible digits because of the rule of product. The rule of product is that, given a list of steps, if there are a choices at one step and b choices at the next, then there are a times b different sets of choices to make.
Ooh.
Similar to the remaining digits from before, the central digit can assume any value between 0 and b minus 1 inclusive, bringing the total possible palindromes for a starting number n with y digits to be equal to b minus 1 times b to the y. The mirror method turns our y digit n into either a number with 2y plus 1 or 2y plus 2 digits, because we double the length of the number by adding n and its reverse, then add either 1 or 2 digits in the center. If we want to know about how many palindromes there are with x digits without knowing the starting y value, we can set x equal to 2y plus 1 and 2y plus 2 and solve for y as y equals x minus 1 over 2 and y equals x over 2. Based on our definition of the mirror method, the amount of numbers with 4 digits should be the same as the number of those with 3, 6 with 5, 8 with 7, and so on. To get this effect, we can take the first y equals x minus 1 over 2 and floor the result so that the result is the same for each of these pairs. Plugging back into our equation from earlier tells us that there are b minus 1 times b to the floor of x minus 1 over 2 possible palindromes with x digits, which we can verify with our table from before. We'll use this formula in a second to answer the question we had from before. Does the sum of the reciprocals of every palindromic number converge to a finite number? Before we answer this question, let's make a graph of what this sum looks like in base 2. Those familiar with Calculus 2 would know that we can represent our sum as the total area of all these rectangles as we go to infinity, but it looks like
This is a log scale on that y-axis. No? Yes. Well, if it still looks like this, though... What's actually being graphed? Did I miss that? So... I'm thinking of the sequence 1 over n looks something like this. But if you graph it on a log scale, it's going to look different, isn't it? Let me back up a little bit.
Before we answer this question, let's make a graph of what this sum looks like in base 2. Those familiar with Calculus 2 would know that we can represent our sum as the total area of all these rectangles as we go to infinity, but it looks like there's no meaningful pattern that lets us easily evaluate this series converges or diverges to infinity. Since we don't know where each palindrome will end up, we can try to make an overestimate and see if that converges. If we make infinitely many rectangles that have a larger total area and evaluate that their total area converges, then our original series must also converge. If we were to look for the largest jumps between numbers, we'd see that they occur when the amount of digits increases, and the next number after the jump is always represented by a number that starts and ends with a 1.
I may be worried about nothing, Ming. I was just looking at the y-axis and seeing it's expressed in powers of 2. I don't know. I might just be overthinking this. I guess it probably solve the same kind of general shape. And I'm just worrying about nothing, but yeah, I'm just wondering why the y-axis in powers of 2, I guess.
And is filled with zeros. Since we know how many palindromes there are for a given amount of digits, we can determine the horizontal distance between each of these points as being b minus 1 times b to the floor of x minus 1 over 2, where x is the amount of digits. Then, since we know this number always increases every odd digit, we can add together every group of equal horizontal distances to remove the need to floor our digits. If we can extend each of these lines up to meet the biggest number in each group, we'll make infinitely many rectangles with heights of 1 over b to the 2n plus 1 and a width of 2 times b minus 1 times b to the n. The height comes from the fact that we know the biggest palindromic reciprocal in each group is the reciprocal of an odd digit number that starts and ends with 1. Now that we know this, we can write this situation using sigma notation as our overestimate a is equal to 2 times the sum from n equals 1 to infinity of b minus 1 times b to the n divided by b to the 2n plus 1. To know if our overestimate converges, we need to perform 2 tests, the limit comparison test and the geometric series test. The limit comparison test is as follows. Let S be the series S equals the sum from n equals 0 to infinity of a sub n, and S prime be the series S prime equals the sum from n equals 0 to infinity of b sub n. If the limit as n goes to infinity of a sub n over b sub n equals a number c between 0 and infinity exclusive, then S and S prime will both converge or both diverge. Then, the geometric series test is as follows. If a series S is equal to the sum from n equals 0 to infinity of a times r to the n, where a and r are both real numbers, then S will converge if the absolute value of r is less than 1. Otherwise, it'll diverge. Using these 2 tests, we can prove whether or not our overestimate converges. We can set our first series A equal to the sum from n equals 1 to infinity of 2 times b minus 1 times b to the n divided by b to the 2n plus 1. And a
I feel like I'm pausing this video a lot, and I'm sorry if that's annoying. That bit about... I almost wish the person found an intuitive explanation for this instead of just outright saying limit comparison test and geometric series test. I think it'd be nice to avoid the heavy analysis stuff if we could, because before that it's hard to follow all the algebra, but at least it is just algebra. I don't know, but there might be a payoff later on if we do accept some more complicated types of math. So I guess let's give it the benefit of the doubt.
a prime to 1 over b to the n. If we take the limit as n goes to infinity of 2 times b minus 1 times b to the n divided by b to the 2n plus 1 divided by 1 over b to the n, we see, after some simplifying, that this converges to 2 times b minus 1, which will always be between 0 and infinity as long as b is a real number. Now we know by the limit comparison test that both series will have the same behavior, either diverging or converging. Next, we can use the geometric series test to prove that a prime converges. If we set r equal to 1 over b, we know that a prime will converge because 1 over b will always be less than 1, since we are only looking at basis b where b is greater than or equal to 2. So, since a prime converges and a prime pass the limit comparison test, then we know that a must converge. And since a is our overestimate, then we know that our original infinite sum of the reciprocals in every base must converge as well. If we plot the sum of the reciprocals...
Well, so is limit comparison test necessary? Couldn't you just have done comparison? I don't know.
Of the first 1,000 palindromes in basis b, we see that they fit along this curve, which is approximately equal to 6.4 times b minus 0.7 to the power of 1 over 10.6 minus 4.6. Before I end the video, though, I want to talk about one last pattern that was the other inspiration behind me making this video. If we go back to the numbers generated from the mirror method and zoom out, a pattern seems to emerge that doesn't seem that obvious at first. To define this pattern, I want to focus on odd-digit palindromes to make what I'm about to talk about simpler. This pattern allows us to generate palindromes with an odd amount of digits in a recursive manner in a visual pattern that doesn't require the underlying numbers used to generate it, only different colors. To start, we'll define our base case as P of 0, which is a grid with 1 column and b rows filled in ascending order from 0 to b minus 1. P of n is then generated by making a grid with b minus 1 times b to the n rows and 2n plus 1 columns, and splitting it into b minus 1 groups. In each group, set the outer walls to be equal to the same number between 1 and b minus 1 in ascending order per group. Then, place every previous p of n minus 1, p of n minus 2, and so on till p of 0, from the bottom to the top on top of each other, lined up along the center. As I wrap up the video, I'll show what this pattern looks like in base 2 and base 3. If you're still watching, thank you for listening to Ramble. This video was entirely animated, edited, and composited in Blender, mostly using geometry nodes, so if anyone is interested in seeing the process behind its creation, please let me know in the comments.
Those are pretty
This is my
fun
first time
patterns,
doing something like this,
aesthetically.
so any feedback is appreciated. Thank you.
Hey, Atishay. So this is, the YouTuber 3Blue1Brown has an annual summer math exposition competition where people can submit videos to be reviewed by the public. And so that's what we're doing right now. We're going through submissions and trying to offer good feedback on people's videos. Okay, what to say about this? A little all over the place. I was finding it hard to follow. The algebra, like, this is just a lot. 3Blue1Brown really has a talent for, like, helping you through this type of stuff that I don't know how to do myself, and I think most people don't know how to do. And he usually skips it, but in an elegant way where you don't feel like you're missing out on details. But I don't know, as much as I generally don't like this again feels like kind of a hobbyist. Ooh, what did I do? Okay. Sort of problem. I do enjoy thinking about different bases, and palindromes are fun enough. Like, I like them more than like magic squares. I'm thinking it's going to be in the 5 range for me, somewhere around 5, like 5 plus epsilon. What was the intended audience? High school and undergrad? Okay. Like, what kind of was the payoff? Like, what was this graph at the end here? I didn't quite catch it.
Their overestimate, then we know that our original infinite sum of the reciprocals in every base must converge as well. If we plot the sum of the reciprocals of the first 1,000 palindromes in basis B, we see that they fit along this curve, which is approximately equal to 6.4 times b minus 0.7 to the power of 1 over 10.6 minus 4.6. Before I end the video, though, I want to talk about what...
Like, I don't know. It's, yeah. Which, that's what I'm thinking too. It's a little anticlimactic. Yeah, algebra details, I definitely can be omitted. I definitely want to see the setup though, at least.
Hey Don, I'm
Yeah.
back, but with the worse mic.
Oh, hey, Leo.
Don't mind me. I'm
Okay.
just hanging out.
You're
Shh, shh,
the neutral cop
shh, it's
now.
okay. Shh, don't worry.
You don't think a math video should have computations at all? I appreciate seeing the setup in the conclusion, at least.
I don't think there should be math videos at all anywhere.
Yeah. Let's go back to pictures.
What's the point of it?
So number 3 had to click me unless the result is highly surprising. I'm never much of a number theory person either.
Oh yeah? Name every number.
Hey, Harmony Hype. The video starts with an interesting premise. What happens if we look for palindromes in different bases?
I don't
Fuck
know.
number
What
theory.
happens?
Well, if you were paying attention, Leo, you would have learned. Well, kind
I
of.
wasn't. I would have kind of learned, or I would have learned.
I don't know. It depends how many times you pause the video and rewatch it, I guess.
Yes, that's true.
Welcome back, say stuff. My best friends are numbers.
I don't know if they consider you friends. It's like my best friend's a number, and the number shows up in chat. It's like, I'd say we're acquaintances. It's like, oh man, it's not even the goddamn number.
Ugh.
Number palindromes in differing bases. All right, well, I've done my little chore, which put me on this account. So now I'm free to just harass you.
Yeah, you can harass me even more effectively than usual since you're in voice now.
Yeah, it's just the same as me in chat, but now it's like forced upon people. There's no escape. Yeah, just close your eyes or be in Twitch chats.
Gotta write an AI that selectively mutes your part of the audio.
Yeah. Good luck. I have many voices. Try all as you might. Thing's still here. Yeah, I just opened the stream. I didn't have it open. Hi, Ming.
To avoid using.
Well, Ming, what do you even though I have to go in like 3 minutes. What do you think about all in analysis, all of these weird counterexamples? I was reading about one today, which was an example of, they call it a trigonometric series, but it's basically like a Fourier series where you have some Cn e to the inx. And it doesn't converge everywhere, but converges almost everywhere. And it converges to 0 almost everywhere. But not all the coefficients are 0. So it's like having non-zero Fourier coefficients, but still converges to 0 almost everywhere. The set where it doesn't converge is actually like a really weird generalization of a Cantor set, where you remove the middle half, then middle thirds, then middle quarters, etc., etc. And I was just thinking, like, how do I put this? I don't know how I feel about a lot of these counterexamples, because some counterexamples, especially like the ones in topology, are really like, I feel like they teach you more about your model of spaces than about something about the phenomena. Because lots of math, you invent these objects that you want to be general enough to talk about what you care about. But sometimes they're so general that there's like weird things that happen. And when those weird things that happen is like, if you're a Platonist, should you believe in those weird things as a real thing or as just like a side effect of the type of like technology you're using? And with a lot of stuff with the counterexamples and analysis, you know, I guess I just have to think about them more because maybe there's both in that, where like some of them I would think of them as side effects of the invention and some of them reflect real weirdness in the phenomena. Yeah, I was reading about sets of uniqueness today. I don't know much analysis, and so like, but it was interesting. Uh, and uh, and I also learned like the Toeplitz summation trick, which was pretty cool. It was like sort of a way to do summation by parts tricks. It was used in proving some cases where the empty set is a unique set. Typewriter sequence doesn't satisfy Borel-Cantelli, for instance. See, I don't know what this is even. Well, I think I knew what the Borel-Cantelli lemma was at some point. Yeah, well, yeah, I'd have to learn more of the analysis, or I guess relearn or whatever. Because the thing with the analysis, with the topology ones, I feel like I have a better feel of like when it's like, oh yeah, this is just a thing that has to do uh with the technology we're using. Like we can change our axioms and this would go away. With the analysis, maybe I just don't know it as well, and so I have a hard time telling which one is which way. But yeah. What are the fun analysis counterexamples? More of an instrumentalist? Oh, well, you gotta play the music, Ming. Don, do you have opinions on the various analysis counterexamples?
I mean, so I was not listening at all to what you were saying, to be honest, because I was
I wouldn't
typing
listen
out
to
my
me either.
feedback. And you know how I am with listening to you in general, yeah.
Yeah, no, that makes sense. I wouldn't listen to me either.
But would like the wire stress function be an example of what you're talking about?
Yeah. Wire stress function, absolutely.
I don't have a problem with them. Like they are crazy, but I think
No, it's not like whether you like them or not. It's like, how would I say this? Suppose somebody came to me and he was like, "Hey, there's this really weird thing I learned about cars that if you do this to this car, I don't know, it explodes." And I was like, "Okay, well, that's just something that happens with a Nissan Altima. That doesn't really tell me something about cars in general." Sometimes with counterexamples, I feel like it's something that like, okay, you've set up, it's like you've built your car and you get these side effects out that come from the way you built it. But it doesn't apply to like you could build it another way and you wouldn't get those side effects. And sometimes it feels like, oh, this weird counterexample really is something that tells you something deep about the theory that you want. And I don't have a great feel for what way I feel that way for a lot of the analysis results, whether it's like of the invention or of the phenomena. Cantor's function. Is that like you can put like a measure on a Cantor set?
Oh, I've heard of Devil's
And
Staircase.
yeah.
I forget how that looks. No, I mean they have an important place in math. Like I never, like, it can be annoying to be corrected, but like math is ultimately like all about being precisely logically correct. So I don't know.
No,
It feels like
it's
the time and place to do that.
maybe I'm not expressing what my problem is with it well. Well, maybe my problem with it is not even very well defined.
Yeah, I feel like you're talking more like an applied math person. Like I feel like we should have switched roles here.
And non-measurable sets. Yeah, well, there's like I also learned about Bernstein sets, which were interesting.
Okay.
Anyway, well, I must be off. Have fun, Don.
Okay, bye again. Okay, that was a nice little Leo lecture segment where he took over the stream for like 10 minutes or however long that was. This video feels like a 5. I'm open to adjusting it like plus or minus 1, but I don't know. I feel like it is about the same as a lot of other math YouTube videos I've seen, which is a pretty high bar. Like it's a good video, but it definitely has things it could have done better. Came to function, really? I don't think I've heard of this one. I want to say that Zach, or E2the2iPi, who streams on Twitch, I want to say he's integrated this on his stream once. F prime equals 0 almost everywhere, but increases from 0 to 1. That's kind of wild. Oh my god. This is a disgusting definition for a function. What would be my topic if I made a video? I would probably want to do something with the connection between PDEs and physics. Like, I'm thinking of like energy methods specifically. Or something machine learning-y. I mean, and obviously like mathematical oncology. I don't know what exactly I would do with that, but like I wonder if mathematical oncology is a niche on YouTube that isn't that fleshed out like everything else with math is. I don't know. Continuous at all points in the Cantor set. I've heard of the Cantor set. I don't remember. Hey Zapway. What is that? Differentiate that? I never taken measure theory. Yeah, I've been wanting to what Phobos is saying. I've been wanting to kind of like repackage some of the lectures that I had from my class a few months ago. Because there's a really cool way to do clustering, so unsupervised learning, if you just know like some bare minimum graph theory and a good amount of linear algebra. Let's see what Zapway linked. By the way, Zapway, I don't know if you have another shift coming up at some point, but that Zapway has also done this review-a-thon, I think 2 days ago. Oh yeah, that'd be awesome, Ming. I guess we can talk more about that. No worries, Zapway. To be honest, I kind of struggled in my PD's class, but what I could figure out, I really loved. What am I looking at here? Okay, I don't have an easy way to actually like run this, but you've actually like worked on the Cantor function and stuff. That's cool. Cantor, not Cantor. You just had to come in to correct me. Typical internet person. So animation makes you think, is the inverse of Cantor function a simple one? I wouldn't think so. Yes, we... Are you Bob the Builder? Oh, nice. Yeah, Leo lectures hijacked the stream a bit to talk about weird analysis counter examples, and this one came up. The extension of the fundamental theorem of calculus claimed by Harnack. I know Harnack's inequality. Okay, anyway. Any bets on when Leo will... We should make a probability distribution for when Leo will pop up in stream. Okay, I think I think I'm putting this out of 5. Oh, okay. Time has flown by. I have 30 minutes left on my shift, and then we're gonna hand it off to Walking Stick Library, is my understanding. Let's see. So we got to be mindful of the time. Ooh, is this gonna be asymptotic? Or no, Fourier series. How long are you? Ooh, we have time. Okay. This will be pretty good timing, I think. 18 minutes to watch, 10 minutes to review. Yeah, exactly. Exponential distribution. Divergent series creating something from nothing. This makes you think of asymptotic analysis, but maybe this is going a different direction. Divergent series, how they arise naturally in Fourier series. Upper division undergrad or beginning grad student in math. Okay. Are PhDs allowed... Like, in the competition, summer math exposition, anyone is allowed to... Anyone who makes math YouTube videos, or anyone who doesn't and wants to make, like, a one-off math YouTube video. Like, it's open to anyone who wants to submit a video. I think they're closed for this year. Submissions are closed. Anyone can be a judge, too. It's open... Oh, sorry, I muted my mic in my hotkey. Switches the tab on my browser. Energy, sorry, but I'm not. Today is just a video group watch review day. On Thursday, I'm planning to do a stream, but the first 2 hours probably won't be taking questions either. You've watched them before? Oh, cool. I never used to have allergies, and I now have like seasonal allergies. It's normally in the spring, or if I travel somewhere else. Actually, I get allergies. It's kind of annoying. Okay, I think we're ready to watch this. Oh, that's cool, Ming. Oh, I need to drop the link. Okay. Start it off there. See if we'll need to adjust it. He talks too fast, but he's cool? Okay. Let's see for ourselves.
Suppose that you owned a precious stone, and you loaned it to a museum periodically. One day you would have the stone, and the
Periodically.
next you would get it back from the museum, over and over ad infinitum. How much of the stone do you have at the end of this infinite process? This is a question posed by mathematicians going back at least as far as the 17th century. And as rigorous as mathematics of the time was purported to be, different mathematicians found different answers and justified their answers with metaphysical arguments. Written out as a mathematical expression, we would have +1, -1, +1, -1, +1, -1, etc. This is called the Grandi series, named after Giotto Grandi, who studied it in 1703. Today we call this a divergent
Bit of
series,
space.
but back then mathematicians didn't have strict rules.
I feel like he just saw his kid misbehave. Matthew, you were in Spanish? I mean, that'd be cool. See if I can understand what they're talking about.
On how to assign a value to an expression. Grandi formally demonstrated two different values that might be assigned to the series, 1/2 and 0. And after seeing that the sum could assume two different values, Grandi didn't make the reasonable conclusion that something is wrong here. Rather, in a fit of religious poetry, he declared that this is evidence of the divine, or creatio ex nihilo. Creatio ex nihilo is not a spell from Harry Potter,
It's Leviosa, not Leviosa.
but rather the idea of the creation of something from nothing. However, like Harry Potter, divergent series have been accused of being created by the devil. Specifically, Abel wrote in 1829 that divergent series are the invention of the devil.
Abel said
and
that.
It is shameful
That's
to base
fun.
on them any demonstration whatsoever. A quote that can be found in the preface of G.H. Hardy's 1949 textbook, Divergent Series, from which I gather that Hardy did not heed Abel's warning. Now, up to the mid-19th century, mathematicians made arguments concerning calculus or analysis or fluxions using vibes, intuition, and bubblegum. It wasn't until Cauchy in 1821 introduced a rigorous definition of limits and convergence in his book Cours d'Analyse that we had a rigorous foundation for calculus in general. From his definitions, we ended up getting a clear delineation between convergent and divergent series. And if we would listen to Abel, then we would miss some really interesting ways of assigning values to these series, solving some mysteries of quantum physics, and even earning Fields medals. So today, let's talk about divergent series on that math thing. The study of infinite series began with the Greeks. Mathematicians like Archimedes used geometric series to compute the area or quadrature between a parabola and a line. But outside of geometric series, they didn't have much comment concerning infinite series. The first non-trivial divergent series was discovered by Oresme 1600 years later in the 14th century, when he was studying Euclid's elements and examined the harmonic series. When describing the result of geometric series, Oresme commented, "It is possible that an addition could be made, though not proportionally, to any quantity by ratios of lesser inequality, and yet the whole would become infinite. But if it were done proportionally, it would be finite," as was said. Here, proportionality refers to the geometric progression in a geometric series. There isn't much about the use of divergent series before the time of Euler, but Leibniz and the Bernoullis did correspond about the Grandi series in particular. Leibniz appealed to the idea of probability to arrive at the answer of 1/2, which he justified with metaphysics. In particular, he said, "Furthermore, this kind of argumentation, even if it seems more metaphysical than mathematical, is nevertheless sound.
Oh, he stumbled.
And otherwise,
on
the
his words.
canons of true metaphysics are of greater use in mathematics, in analysis, in
I like that.
geometry itself, than is commonly supposed. Whence it comes about that in continuous things, the exclusive extreme can be treated as the inclusive one." So again, vibes and bubblegum. This quote comes from Hardy's Divergent Series, and he had it in Latin in there, so I used Google to translate it. So if it's not exact, I mean, I haven't studied Latin in a long time. Now, Euler also did play with divergent series. In fact, he has such a large number of results utilizing divergent series that he really seemed quite their advocate. Often he would appeal to the method of able summation, where he would take a series, use the series as the coefficients of a Taylor series, and then try to find the sum of that Taylor series and assign a value to it. So, for instance, if we take 1 minus 1 plus 1 minus 1, this can become 1 minus x plus x squared minus x cubed plus x to the fourth, etc. And we recognize this as the geometric series, so we can go ahead and replace it with 1 over 1 plus x. And we recover the sum, formally at least, by setting x equals to 1, which is actually outside of the domain of definition, but we'll try it anyway. And the result is that we see that the Grandi series kind of equals 1/2. Now, you might feel like this is a solid answer, like many of the mathematicians of the 18th century. However, this isn't the only Taylor series that would formally give us the same divergent series. For instance, if we consider the rational function 1 minus x squared divided by 1 minus x cubed, or when it's simplified, 1 plus x over 1 plus x squared, this has a Taylor series of 1 minus x squared plus x cubed minus x to the fifth plus x to the sixth, etc. And
this is a cursed Taylor series. It skips every, third term? Huh. Analytic continuation? There might be something like that here, yeah. Theta minus 1 is equal to minus 1/12? Not yet, but maybe.
And if we replace x with 1 here, well, we also get the Grandi series, but the rational function becomes 2/3. So we already have two different Taylor series.
Well, there's no x and there's no 7th either. So I assume it's not a typo. It's probably not multiple typos at least.
Would equal different things. I mean, usually this is why we just sort of stick to the regions of convergence, because you don't run into this problem. Well, this isn't actually the only way to sum divergent series. Another way we can explore this series is through the average of the partial sums. The partial sums of the Grandi series are 1 and then 0 when you have the minus 1 to cancel the first one out. Then you add another 1, so that gets you a 1. So you go 1, 0, 1, 0, and so on. And if we average these partial sums in the limit, we obtain 1/2, which is great. But then Bernoulli discovered that if you add nothing to the series an infinite number of times, as say 1 plus 0 minus 1, 1 plus 0 minus 1, 1 plus 0 minus 1, etc., then we get something different. Intuitively, you would expect nothing to have changed because all we did is add zeros. But Bernoulli demonstrated that when you average the partial sums here, you get 2/3. So both these methods could give us either 1/2 or 2/3, and so we get different
really
values
based
on seemingly arbitrary decisions. And that's not to mention obvious regrouping of the terms, where we can place parentheses around each pair of +1 and -1, and then all of those would just cancel to 0, and then the sum would just give us 0. And in fact, that's what Grandi himself did. He performed both the able method and the regrouping method here to get both 1/2 and 0. And from this, he declared that this is mathematical evidence for creatio ex nihilo, or the creation of something from nothing. I suppose Bernoulli's idea of adding an infinite number of zeros to then increase the sum from 1/2 to 2/3 would also be an example of this creatio ex nihilo. But that is the weirdness of divergent series, and why many mathematicians steered well away from them for centuries. As Hardy describes it, the central issue here is that mathematicians at the time didn't ask questions like, how do we define the Grandi series, but rather, what is the value of the Grandi series, already making the assumption that there is one. For the modern mathematician, we don't assign a value to something until we can first define it. The former is the sort of thinking that led great mathematicians like Leibniz to appeal to metaphysics for their answer. Augustin Cauchy, in 1821, gave us the Cauchy criterion. If we first define the sequence of partial sums as Sn, the Cauchy criterion says that for any fixed epsilon greater than 0, the series is called convergent if the difference between Sn minus Sm is smaller than epsilon for all large enough n and m. And this gives us a concrete distinction between convergent series and divergent series. Convergent series are the ones whose sequence of partial sums converge to a finite value, or at least in the case of it being in a complete metric space. The Grandi series gives us partial sums that alternate between +1 and 0, and hence we don't assign it a value, at least not according to Cauchy. And in fact, Cauchy even makes a statement in his book saying that maybe he's being a little bit harsh by saying that we can't assign a value to everything. And we have just seen how difficult it is to assign a value of some kind to a divergent series, which in some sense makes them useless. However, despite this apparent uselessness, the investigation of divergent series and methods to assign them a value have led to a lot of interesting mathematics and helped resolve a lot of questions in terms of Fourier series and even a little bit in quantum physics. So let's talk about some of these results. So the alternating series of ones is a divergent series that if you were trying to come up with a divergent series, you'd be pretty easy to think of. However, it's artificial in the sense that we just sort of dreamed up the series and it didn't arise naturally in the pursuit of some other different mathematical or physical problem. However, mathematicians who previously didn't think much about divergent series had to seriously confront them at the beginnings of the 19th century. This is because Fourier, in his pursuit of a nice solution to the heat equation, invented Fourier or trigonometric series, which breaks up a periodic function into a series of sines and cosines of differing frequencies. A Fourier series really shook mathematics to its core, and mathematicians had to rethink everything all the way back to how they define a function or even the real numbers, just to describe them. The first mention of functions as a concept goes back to Leibniz in the 17th century, but they weren't functions as we think of them today. Essentially, mathematicians viewed functions as expressions and equations that produce a value. But to define a function piecewise, for instance, was generally not done or not permitted. However, Fourier showed that even for piecewise defined functions, they could still be expressed as a single Fourier series, which then makes these sort of piecewise functions expressible as a single expression or equation. Other aspects of Fourier series led to the development of set theory and rigorous definitions of the real numbers, which we've talked about previously on the channel. Truly, there may not have been a more impactful work of mathematics than Fourier's The Analytic Theory of Heat, published in 1822, but based on his work in 1807. In his work, Fourier expressed the series for the function f of x equals x with x between minus pi and pi, and then repeated periodically thereafter. He declared that this alternating series, here with sines of nx over n, converged to f of x, and he said it was not a question of faith, but of mathematics. However, as I said before, mathematics at the time wasn't propped up by rigor, but by vibes and bubblegum. Lord Kelvin referred to Fourier's work as a great mathematical poem, but even though Fourier's work won him a prize for resolving a mathematical description of heat, the award committee said that Fourier's work leaves something to be desired in the realms of both generality and rigor. Honestly, not exactly the kind of review you'd want your work to receive. Turns out, even for simply continuous functions, this is not such an easy question to answer. Dirichlet is credited as the first person to
Is that how it's pronounced? Dirichlet? I thought it was Dirichlet.
Give somewhat broad criteria for the convergence of Fourier series. Dirichlet found that if a function was integrable and of bounded variation, which means it doesn't wiggle too much, then the Fourier series converges to the average of the left limit and the right limit of a function at the point x. This means we can immediately declare that the Fourier series of a continuously differentiable periodic function converges to the function itself. So overall, good news. But it doesn't actually give us any guarantees for simply continuous functions, which isn't good news. And Dirichlet wasn't able to extend this result to general continuous functions. In fact, Paul Dubois-Reymond demonstrated in 1876 that there are actually continuous functions whose Fourier series diverge at...
Neil Patrick Harris with a beard. Tell me I'm wrong. Sorry.
a single point, and this was later expanded to a dense collection of points. So Dirichlet's result was a sufficient condition to guarantee the convergence of a Fourier series. So the question is, what other conditions can we impose on functions to get convergence? Nikolai Luzin conjectured that Fourier series for L2 functions would converge almost everywhere, and this result took until 1966, within living memory, to be proved by Lennart Carlsson, who won a Fields Medal for this work. In a 2007 interview with Carlson by Rosen and Scow, sorry if I mess up your names, Carlson said this about solving the problem. I tried for some years and then I forgot about it before it again came back to me. Then, in the beginning of the 1960s, I suddenly realized that I knew exactly why there had to be a counterexample and how one should be constructed. Then, I could prove that my approach was impossible. I found out that this idea would never work. I mean that it couldn't work. If there was a counterexample for the trigonometric system, it would be an exception to the rule. From then on, it only took 2 years or so. But it is an interesting example of to prove something hard, it is extremely important to be convinced of what is right and what is wrong. So Carlson gave us a very general condition for the convergence of Fourier series. However, it doesn't say that the Fourier series of an L2 function converges everywhere. It says almost everywhere, which means that it is vanishingly unlikely to select a point where the series diverges. But that divergence may still happen at an infinite number of points. In fact, Katz-Nelson in the same year demonstrated that for any measure zero set, there.
Dr. Gold. Thank you so much for the raid. I hope your stream was good. I want to get back to the video in a minute here, but I really appreciate the raid. Welcome in, people. If you're confused about what's happening, this isn't a normal stream for me. Normally I do math help just like Dr. Gold, but today's a special day where we're reviewing summer math exposition contest videos. And so you come in towards the end of a video about divergent series. You had fun? Oh, cool. Yeah, this has been really fun. Earlier we had like 3 other people in the Discord call too, helping out and like voicing their opinions. Yeah, I'm gonna hit play on the video. We're going pretty deep into math by this point of the video. We're talking about like Fourier series and things like that now.
Is a continuous periodic function whose Fourier series diverges at all of the points of that set. What that means is that the points of divergence of a Fourier series of a continuous function could actually be all rational points, which is a problem for us since we only compute at rational points on both computers and by hand. So this leaves a question of how do we handle these points of divergence? Let's look back at our Grandi series. We saw that if we took averages of our partial sums, that what we call a Cesaro mean, then we get an answer of 1/2. In fact, if you take a convergent series and take its Cesaro mean, then you'll get the same answer as the sum of the series. So this is a little bit more general than summing any convergent series, but also can sum convergent series and some divergent series, which is great. And if you then take the Cesaro mean of the Cesaro sequence, then you actually get the same answer back again. So it has some sort of consistency to it as well. Now, if we have a divergent series, we say it is Cesaro summable if its Cesaro mean converges. And through this, we have extended the notion of convergence beyond that given by Cauchy. It's exactly this perspective that it's best to examine Fourier series. In fact, the Hungarian mathematician Lipó Fehér managed to extend Dirichlet's result from continuous functions of bounded variation to all continuous periodic functions, but not in the case of regular convergence of series, but using Cesaro convergence. Having methods for resolving divergent series or Fourier transforms is important not only for mathematics, but also for engineering, which really demonstrates the power of this different perspective of summability, which I think is really cool. And honestly, having methods for resolving divergent series for Fourier transforms is important not only for mathematics, but also for engineering, where Fourier series and Fourier integrals aren't actually well-defined in convergent series of integrals. In fact, when you see definitions like this of the Fourier transform, that's not actually a single integral, but rather a limit of finite integrals that converge almost everywhere, thanks to Carlson's theorem. So since these series and integrals are actually formally, honestly divergent, we need different methods for actually summing them. And that is where Fehérb's method comes in and Cesaro means come in. And so now we know if we want to compute the sum of a Fourier series, we don't want to sum it like an ordinary series, but as a Cesaro sum. So perhaps if you actually lend your precious stone to the museum too many times, you will actually end up with only half a stone. In any case, if you want to see more mathematical details about the convergence of Fourier series, then do keep an eye on this channel. My series of live streams will start up again in a couple weeks, and I can't wait to see more of you. If you like this video, please consider liking and subscribing, and as always, thank you for watching, and I hope you have a great day.
Okay. Yeah, I've never done Sturm-Liouville on its own for its own sake, and I really want to. I've never seen it in its full glory. I've only encountered it tangentially. Okay, so for this video, I really love his presentation style. And his way of speaking is very, like, calm and pleasing to the ear. I don't like the first half of this video feels like it's intended for like a math novice, and the second half feels like it's intended for a late undergrad / math grad student, which is what the overall target is. I didn't mind how much he was showing his face personally. That being, like, I think like the first half of the video could have been its own video, maybe if you have some different payoff. It just felt like a very abrupt shift from one to the other. Like the issue with where does he show it? Really? Why can't I find it? Okay, yeah. So like the first half of the video is kind of all about this divergent sequence: 1 - 1 + 1 - 1 + 1. And then when it suddenly shifts into Fourier, things go off the rails, I think. His manner of speaking and presentation of the material. Thank you for the bit, Famished. Sturm-Liouville problem equals BVP and PDs. Yeah, that's where I was. That's where I had encountered it. I'm not that strong on it though. Yeah, I enjoyed the history parts. I mean, they're just being overly generous. My feedback has been like 1 to 2 paragraphs worth. Where is that one quote that, yeah, even though he's fumbled a bit on the Leibniz quote, was in a charming way. Oh, shows up in quantum too? That's cool. I'd love to at least have a baseline knowledge of quantum physics. Even you don't write 10K interviews? Reviews. It's, yeah, this will be the last video that I review today, assuming Walking Stick Library goes live on time, which would be okay if she didn't. I'm able to like stall, but I haven't checked yet to see if she is live. Okay. Not yet? Okay. Thank you for letting me know. My favorite undergrad math class. That's a good one. I would say our like kind of like capstone classes or like your culminating experience class. Oh, thank you for the 24 bits. I appreciate that, Famished. It was just called Methods of Applied Math 1 and 2, so it was a two-parter. Where we just go over like a more advanced ODEs and like systems of ODEs, which I really love, and stability. Yeah, I was really hoping for asymptotic series also. I was a little like it's a cool direction that he took it. Although I mean, I don't know. I enjoyed the first half and I enjoyed the second half. I just don't feel that they connected as well as they could have. I should write that exactly, I think. I enjoyed the entire video, but the first half felt disconnected from the second half. Favorite non-math class? Ugh. Unless you're willing to count physics, I don't think I had one. I did not like almost any of my non-math classes. I think I'd appreciate an art class more today than I would at 18. I did not appreciate them at the time, though. With mathematical statistics. Ooh, yeah, I did a class called engineering statistics, and that was fun. I want to relearn stats and probability. Purcell review to stall. I don't think I'll do that, but I do have Purcell in my very near future here. Took a graduate advanced mathematical modeling class in undergrad. That sounds amazing. Limit cycle stability, chaos. Oh, I need to learn chaos. I skipped it in my master's. Half the class was just learning how to program in Mathematica, so the side of things wasn't explored. Oh, but Mathematica is really helpful for that stuff, though. To be fair, yeah, but it is unfortunate that you miss out learning more of the math, though. Zeeman heart model. I never heard of that. Double pendulums. Ooh, that's cool. Probability for your master's next semester. Took a basic engineering statistics probability class in undergrad. It was iffy. Yeah, probability it's pretty sick. It just gets so difficult. It'd be cool to learn measure theory and then come back to probability, maybe. That's also a huge undertaking, what I just said. So, feedback. The first half felt disconnected from the second half. The first half was very historical, and I shouldn't say math not novice, but could be at least sort of followed by a high school student. While the second half suddenly jumps to late undergrad / grad level math, which I know is the intended audience. Given that audience, the first half could probably have been skipped / isolated to a separate history focused video. Philosophy about social movements. You were too radical in your debates. You're that student. That's fair, though. I wouldn't have been brave enough. I still wouldn't be brave enough to really voice my thoughts and stuff like that. Stochastic modeling / simulation in the spring. Ooh, that's exciting. I'm excited for you, King Assassin. Itching is very real. Took a class on history of gardens at neighboring school with a friend. We just kind of laughed our way through it. Actually, looking back, it was pretty sweet. History of gardens. That's a wild class I never would have thought existed. Philosophy of religion. That would be cool. Polynomial possum. Thank you for the follow. Probably can come hard really fast. Yeah, it can. Now, some course you enjoyed medieval history or archaeology. I don't think archaeology is STEM. Hello. I hope you're doing well. Those who don't know, Polynomial Possum will be one of our fellow reviewers. I don't remember what day you're going, but I know you're in there somewhere. Tomorrow. Awesome. Did I have anything else to say about this video? Ooh, I did really enjoy the different Taylor series to represent 1 + 1 - 1. That was new for me. Microeconomics as a non-math. Ooh, I did not enjoy any economics classes that I took. I might like it if I can use more sophisticated math with economics. But the basic, like, gen ed ones that I took were not it. I did really enjoy and adding 0 to a series to change its limit. I guess limit in quotes. Hmm. I think it's what I have to say for the feedback part. What are we feeling? Wait, the maximum was 9? I didn't even realize that. I thought the maximum was 10. That's a weird choice. I'm somewhere around a 5, and I feel bad giving 5s to videos, but just the bar on YouTube is so freaking high. If I submitted a video, I would put myself like 3 or below. I feel bad saying a video this good is average, but I don't know. Category has 2 spots. Oh, that's a good point. Yeah. Once his research into novel gardening methods, it was groundbreaking. Obi with the dad jokes. Love it. Okay, I'm trying to figure out if I need to stall or if she has gone live. Can anyone in chat give me a heads up? By 9, it's like I don't know what IELTS is actually. Is that like the personality test? Sebastian Log? Is that his name? Oh, I should say. When I saw the title, I feel like my feedback is not very cohesive. It could be better written, but in response to Destin, oh, okay. You want to give it a 7, really? I don't know. I don't like it that much. No need to stall? Okay, cool. So I'll just send in this vote and then we'll rate out. More details and less broad. Considering how many people were getting lost in the details today, I don't mind having the opposite issue. Title, I was hoping to hear about asymptotic series, but this wasn't a bad direction to take it either. Okay. For good videos to show pictures, very explicit abstract ones. Okay. We did the number, we wrote our feedback. Let's vote and let's pass the baton. Let me get a link for the people in YouTube. International. Oh, okay. I recognize that acronym now, Ming. Okay, so as far as I know, she does not dual stream, so this is only on Twitch. But we're about to pass the baton over to Eileen, aka Walking Stick Library. In this review-a-thon. YouTube $10. So the YouTube stream will end here. Ming, thank you so much for hanging out and for being on the call for as long as you could be. Anyone else who's here on YouTube, I appreciate you, and I hope you have a good night. Yeah, goodbye, YouTube.